Ladies and gentlemen, please join me in welcoming to the stage your MC for the AI Engineer Paris, Developer Experience Engineer, Rauf Chebri.
Good morning, Paris. Does this work? Can you hear me all right? Nice. How's it going, guys? Did you guys enjoy yesterday? If you liked yesterday, today is going to be incredible. You're going to just love it. So I'm very happy to have you here today for day 2. Yesterday was a fantastic day. We had an amazing opening ceremony with Swix and Ben, co-founder of AI Engineers. And we had a great talk also from Mistral AI, who talked to us about the problems that they face in the enterprise world, which I found fascinating. And we also had a welcome party, which was incredible in my opinion. I gotta admit, these are the best moments in these type of conferences, is where you get to meet everybody, where you get to meet attendees, sponsors, and all the engineers and the founders. And you can hear it a little bit in my voice. I had a little bit of a few chats here and there. But these are my favorite moments. So why don't we get started with something? I want you to look at the person on your right and the person on your left, and just take a moment and take 10 seconds and introduce yourself. Let's do that. All right. All right. That's the spirit. That's how I like it. It's super cool. All right, so we have an amazing lineup of speakers for you today, and we're going to cover topics from agents, MCP, open models, generative media, and more. And I've seen some of the talks, and I have to say they're incredible. So you got to be here. But before we get started, I would like to invite CEO of Koyeb, Yann. Woohoo! The mic is not working for Yann. Oops.
So maybe I'll take
it. Oh, yeah, now.
And now I'm back.
Yeah.
All right. So false starts, but here we are for the second day of this amazing event, this conference that we assembled. I want to speak a bit about contents. So you might have noticed we went from 1 track to 5 tracks, which is quite incredible in terms of coordination. We have over 35 speakers coming today, coming from all parts of the world, some who flew over from the US, landed yesterday from Sweden, Emil coming with us just after. And I hope you'll enjoy it. One key thing, the discovery tracks are also amazing. We had over 500 submissions on the CFP, so you will find incredible content. And if you cannot attend these sessions, all of the sessions will be recorded and available on our YouTube channel. So don't fear missing out. You'll be able to see them all. One last thing I wanted to say is to thank you all again for joining us. One thing you need to be aware is Koyeb is a serverless platform. We're providing high-performance serverless infrastructure to simplify application deployments. You'll find a lot of, our entire team on site today. So we have 2 booths there. You're welcome to stop and chat with them. And now I'm going to hand it over back to Rauf for the next stage of this morning.
Thank you, Yann. Let's give it up for Yann. Something tells me that it's not the last time we're seeing him this morning. But yeah, so if you want to have a look at the full schedule, please download the app where you can find everything that you gotta know about all the tracks. So this is the main stage, but we have 3 other stages. We have Discovery 1, Discovery 2, and we have a lot of workshops. And we also have coffee. at the expo offered by our friends from Tinfoil, so please go and check it out. And speaking of the expo, I highly encourage you to also go and check it out and go and meet the engineers and founders that came here to meet you guys and make new connections and find your next partnership or job opportunity. All right, so without further ado, I would like to also thank the sponsors. I would like to thank the gold sponsors, so Sentry, Arize AI, DeepMind, and Algolia. And also would like to thank our platinum sponsors, Docker and Neo4j. And speaking of Neo4j, our next speaker is co-founder and CEO of Neo4j. His work helped investigative journalists crack the Panama Papers and enabled NASA to reach Mars 2 years ahead of schedule, and drove breakthroughs in cancer research and fraud detection and so many more areas. Please join me in welcoming to the stage CEO of Neo4j, Emil Eifrem. All right, let's give it up.
Perfect. Thank you. In theory, the mic is working. I feel like I hear my own voice, so yes? All good? Perfect. Bonjour. That's all the French that I know. My apologies. I have a French chief of staff. I have French investors. My daughter is learning French, so I'll pick it up. For next year, I'll be able to say a little bit more, I promise. So the slide here says the state of AI engineering. I'm not going to talk about the state of AI engineering. I don't think that's my talk to give. I think that's Swix or Ben. I feel like actually Swix did some version of that last night. But I've spent 2 decades of my life in databases and knowledge representation. And so instead, I'm going to talk to you all about managing state in AI engineering. And more specifically, over the last couple of years, we've observed hundreds of projects built inside of big companies and small companies, building AI applications. And I'm going to share some of the observations from that. Last year in San Francisco, I did a very hands-on practical talk about GraphRag and the benefits of GraphRag and how you can get started with that. This talk is a little bit more high level. It's an opinionated view of where I believe the data layer for AI should go. Or in other words, we've identified 4 properties of a kick-ass data layer for AI applications. All right. But before that, let's start with a little bit of context engineering. Who here knows what context engineering is? Raise your hand. The morning gymnastics exercise is going well. Fantastic. Karpad, I think, had a good one-liner for it. Context engineering is the delicate art and science of filling the context window with just the right information for the next step. It was coined by this gentleman, Dex Horthy from HumanLayer, who wrote a really phenomenal blog series called 12-Factor Agents, which I really recommend for those of you who haven't read it. It's a great treatment. And in Factor 3, he talks about context engineering. He has a really, really simple intro for it. Everything is context engineering. LLMs are stateless functions that turn inputs into outputs. Therefore, to get the best outputs, you need to give them the best inputs. So simple. 3 sentences, a really good kind of summary. And he went on and he showed like a Venn diagram of what context engineering is here. And today in this talk, I'm going to focus about the 3 main sources of state in AI engineering. The state out of your RAG corpus, the state out of your agentic memory, and then the state in your application. I call this the state in AI engineering. Okay, but before that, we're going to talk a little bit about a brief history of application architecture. So I'm going to start by bringing you back to ancient times, many, many years ago, before 2022. And we were all building some version of simple CRUD apps. And lots of architectures around, but At some high level, this, I think, was the canonical architecture. We have some UI, we have a backend, we have a database, right? We store data in the database and in object storage. More specifically, we put our structured data in the database. We put our unstructured data into object storage, and then between kind of the UI and the backend, we speak JSON, which is semi-structured data. Very simple, but then something happened, right? ChatGPT was launched end of 2022. That's why we're all here. Swix coined the AI engineer term 9 months later, mid-summer 2023, right? And we all started building chatbots, right? We started building relatively simple chat applications, right, that sit on top of some kind of orchestration layer. We stuck a bunch of our data in unstructured form into what? Into vector databases, right? And so these very simple but pretty powerful applications ran on top of, honestly, a reduced version of our unstructured data, like the embeddings, right? So that's kind of what we did in 2023. And then in a very gross annual simplification, right? It's only been 2 years that we've been doing this, right? 2024 is when everyone started talking about agents, at least talking, right? Debate of how much was doing. Towards the end of 2024, Anthropic launched MCP, which really helped us think through what tools look like and simplify tool access in agents. And so as we sit here in 2025, we can see a stack is starting to form, right? At the top, it's not just simple chatbots anymore. It's a real application, right, with some AI embedded, AI features on the side or at the core of it. The former orchestration layer now consists of one or multiple agents, and of course there's a big debate between single agent versus multiple agents, that wrap prompts, they use tools, they use memory, right? They use one or multiple LLMs as part of that, right? And then we have the data layer, right? So what's going on then in the data layer? The stack is starting to form, but that really is the upper half of the stack. So let's double click and spend a little bit of time on the lower part of that stack. So we started out with vector databases, right? But after a while realized that, you know what? Just querying on unstructured data in a semantic ANN approximate sort of way, right? It's powerful, but it's actually not enough. And so the vector databases realized that, you know what? We need support for structured data as well. And they tend to call it metadata. And you use it in metadata filtering, for example, right? But then at the same time, there's obviously a bunch of other databases around that we started using for retrieval. It's the relational databases, the document databases, and graph databases, for example. And we all said, you know, that whole semantic search thing, that's kind of cool. We're going to add vectors as a feature, right? So here what we have is we have unstructured, like a data store centered around unstructured data, which is adding structured data. And then we have, I don't know, let's call it Postgres, which is centered around structured data, that is adding support for unstructured data, and a database like Mongo, with JSON semi-structured data, that is adding support for unstructured data. So it's a real party down there, and there's a lot of different models. Everyone's kind of adding what the other folks are having, and honestly, it's a little bit of a mess. And the big question then is, where is this going? And we spent a lot of time thinking about this. What's really required in order to have a kick-ass data layer that makes it really easy to write AI applications? And we've identified 4 properties for a kick-ass data layer for AI applications. 4 properties, and I'm going to walk you through them one by one. Okay. So the first property, you can hear how kind of I talked about it in the state of the union of the data layer, right? Where we're going with this. The first property is, I believe that in order to make it really easy to write AI applications, that requires you to be able to have a data layer that in a very easy way manages unstructured and structured and semi-structured, all 3 types of information in a single data layer. And do that well, right? So store and retrieve, of course, but you want to index them, you want to be able to handle transactional scope across them, and all of that kind of stuff. So that is the first property, the ability to handle structured, unstructured, and semi-structured data. Okay, so let's talk a little bit more about unstructured. Let's double and triple click on that, right? Okay, for property number 2, what do we need to do? What do we want to do with unstructured data? So we just talked about how important it is for all to be able to handle all 3 types of data. But, of course, the fundamental currency of an AI application is the unstructured data. That's one of the L's in LLM, large language model, right? But there's another observation that's been happening as well over the last year or so. There's a lot of talk, and you heard it yesterday from Mistral, which is AI applications. They are, well, they're applications. There's a lot of software engineering involved in this, right? And if you want to write an application, you probably want to do that with types. You want to have structures and objects and classes. And if a lot of your information is unstructured, the question then is, okay, so we have an application. That application is handling people. You probably want to have a person class. But then you have a lot of unstructured data in your data layer. And so you need to be able to bridge somehow, take the data out of your unstructured data layer and reflect that in persons and objects and types up in your application so that you have a convenient and good developer experience, right? So how do you do that? So let's talk a little bit about that. Let's say that we have an unstructured source. I'm not sure if you can read it in the back here, but we have some kind of text, maybe out of our RAG corpus, which has 3 sentences. Andreas is here today. He is a carpenter. Shout out to ABK, right? 3 simple things. So step 1 here is to identify the entities, the concepts, the things out of that data. That's called named entity recognition. It's a technique that has been around for a while, actually, quite a while. And we identify Andreas and he and ABK. And then you can look at this and you can see that the people here, the human beings, we can read this and instinctively we feel like this is probably the same individual, Andreas and he and ABK. So how can we resolve that? How can we figure out a way of combining these things? That is called entity resolution, and that's the next step, resolving these into a single entity, right? Entity resolution. If you look at this data right here, it's actually structured data. This piece we can easily reflect up in our objects in our application state. This process right here, the named entity recognition, the entity resolution, is going to be a really important part of writing applications in a convenient way for developers on top of unstructured data. So the second property of a kick-ass data layer for AI application, I believe, is the ability to consistently and reliably extract entities out of unstructured data. So that's the second one. Okay, the third one. So let's say that we're building an application, and that application is for an online furniture shop retailer, right? And you can see the application. We have some kind of a central part where we have a product gallery of some sort. It has some weird Nordic name for the table, the Kiroda table, right? And then we have an AI-powered community forum on the side. We probably have some kind of an AI bot helping out with assembly instructions, right? The data layer of this might look something like this, where we have a product database, right? We have the purple boxes in here. We have some kind of a bill of material table. We have kind of a product issue tracker table, and they're kind of joined up in some way. But that assembly bot that helps out with assembly instructions in the community forum, well, it probably needs to read data out of some product brochures, some assembly guides, right? And so we put that in there as well, and we've extracted the central entities out of that unstructured data, like we just talked about. So that's the first piece. But then we have this community forum, where there's a lot of chatter, right? And people are talking, they're logging on, they're maybe asking for help, they're commenting. And there's individual chat history memory, but we've also extracted entities. And in particular, we're focused on the entities that are globally interesting. In this case, we have a user called ABK, who's a carpenter, and he wrote that, you know what, for the Kiruna table, the assembly instructions weren't really great, but when I applied 2 drops of wood glue to the table step, to the table legs before step 8, then all of a sudden I could easily assemble it. So of course, when we look at this, we would like our AI assembly bot, right, to be able to answer questions not just based on the data over here, but also out of some of the stuff out of our agentic memory, right? But of course, the problem we end up with here is that we have multiple Kiruna tables in here. So in order to really be able to answer not just with the data out of the assembly guide, but out of these instructions, we need to be able to link them together. There are two ways you can link them together. One is linked during retrieval time, right? So you query across all your data sources. You want to find the Kiruna table, right? And you do that in retrieval, and there you go, right? That's one way. The second way is you do it in some kind of a unified layer where you link it together in the data layer of the stack. I think the second is going to be by far the most powerful for most applications out there for three reasons. The first one is performance. If you do multiple retrievals across multiple of tools, you will frequently end up with dependencies between those retrievals, which adds up the latency. You also have to manage intermediary results, which frequently ends up being relatively big, actually. You re-implement joins in that application layer, and it adds a lot of memory requirements. So that ends up being tricky. When you have real production type deployments, for trivial small stuff, it's always doable that way. The second reason is, we just talked about this, actually it's high complexity. We spent 15 years trying to implement joins well in the Neo4j database, and we're still working on it. It actually is pretty non-trivial to make that work well. And then the third, there's actually a reliability piece. Imagine that there was like a trademark dispute or something like that for the Kiruna table, right? And then we have to change it, right? So if we have to change it, then all of a sudden, in this world, right, we have to do some kind of a text search across all of our data sources, right, and update them, which is entirely doable. But we all know that that kind of stuff is a little bit messy, especially in production, especially at scale. If you have it all linked up in the data layer, it's a trivial change that automatically propagates across the entire state in your AI application. So I believe that the third property of a kick-ass data layer to make it really easy to write AI application is an ability to link entities across persistent agentic memory and into your application data, which tends to come out of your RAG corpus. So that's the third property. And then the fourth property, speaking of the RAG corpus, if we go back to prehistoric times again, we think about the CRUD app. One way of thinking about this is that it has structured data and unstructured data in the data layer, which I talked about. Another way of thinking about this one is that all the data in here is first-party data, right? So what do I mean by that? What is first-party data? Well, in this context, in the context of application development, first-party data is the information that your application directly collects from its own users. It's data that you own. And a couple of examples, profile data, right? The names that people type in, their preferences, that kind of stuff. But also activity data, how long time did you spend on various things, right? Transaction data, those kinds of things. And if you think about to that CRUD era, basically all the information for most of those apps was first-party data. I'm sure there were some integrations and stuff like that, but by and large, most of it was first-party data. But then if you look at our more modern AI app, and we see that the first-party data really sits here in the purple boxes. But the yellow data there at the bottom is actually derived data. It's coming out of the RAG corpus, the assembly guides for the Kiruna table. And what this presents an interesting tension. Because on one hand, this is fantastic. We want to commingle first-party and derived data so that when we reflect that state up into your application, the Kiruna table has the Kiruna table object in your TypeScript application has all the relevant information for it. That's the best developer experience. It also leads to better queries and retrieval. So we want that. The flip side, though, is we have to treat them differently. And a great example of this, we have to have the ability to treat them differently. A great example of this is, what if that trademark dispute thing happened and we wanted to change the name of the Kiruna table? Or maybe we wanted to add to the instructions, right? People handle this differently in RAG, but a very common pattern, probably the best and simplest pattern today, is that you drop all the derived data and you recreate it when the RAG corpus changes, right? Some people try to apply change sets and stuff like that, but I think that's tricky in reality today. So then we would drop all the yellow stuff, right, and recreate this when the RAG corpus is updated, which is great. But if it's co-mingled with the purple stuff, you don't want to accidentally kind of cascade across that and delete some of that information. So the fourth property of a kick-ass data layer for AI applications is the ability to disambiguate between first-party data and derived data, so that we can handle it differently in the application. It'll be different in different types of application because people have different strategies for it, but it's always based on this ability to know, is this first-party data or derived data? Okay, so we've gone through a little bit of history. We've talked about these 4 properties of a kick-ass data layer for AI application. Properties that are required, I believe, in order to make it really convenient to write great AI applications. It's the ability to handle structured, unstructured, and semi-structured data. It's the ability to extract entities from unstructured data, to link them between both agentic memory and your RAG corpus and application state. And then finally, the ability to disambiguate between first-party and derived data. So, I don't know if any of you are work in big enterprises and you're buyers of application software. I think I've seen this many, many times happen where someone is in front of me, a salesperson, and they talk about, okay, here are the needs that you have. And then magically they show up with a product that solves exactly those needs, right? So that is not what we're trying to do here. These are our objective, intellectually honest observations. We don't have this at Neo4j today. But the reason why we're here, the reason why we spend so much of our cycles focused on AI engineers is that this is, of course, where we want to go. And as the CEO, I think I have some amount of influence, at least, over the product roadmap. So this is exactly what we're building towards at Neo4j. So let me give you a little bit of a quick demo of the first 2 principles, which are not perfect yet, but they're really making progress really fast, and what it looks like in Neo4j. So imagine that we have a Wikipedia page that we want to, as an example of unstructured data, that we want to add to the database, and we're going to see our ability to look at structured, semi-structured, and unstructured data in one platform, and the ability to extract entities from unstructured into structured form. So in theory, this should work. So here we have the Wikipedia page for Paris, right? We take that and we copy-paste the URL. We go into the knowledge graph builder here, which will upload it, and it's going to start processing. So a couple of things will happen right now. We start processing and chunk up that Wikipedia page, and we put it into the graph in 2 forms. The raw data, the chunks, but then also the extracted entities. And what you can see here is both of those things at the same time. We're going to remove the entities for a moment, and here you have the raw unstructured data. These are the chunks of that Wikipedia thing. But much more interestingly, of course, are the entities. Those are the ones that mean something to us, to humans, to applications. So here you see that we've extracted like some demographic data. It's too hard for you to see, but it says British citizens and US citizens in the city of Paris. It's in the country of France. And then it's automatically extracted notable individuals, right? So these are the, whatever this color is, greenish, something color. You can see a bunch of really notable individuals out of Paris, which is a very humbling list of people, by the way. This is Igor Stravinsky as an example right now. So this is all automatically extracted from that unstructured source. And you can imagine that once you have these entities, it's really easy to reflect them out into your application state in terms of typed objects. It's also really easy to query across them in a semantically useful way. So those are the two properties at play here, as an example. So that's it for me. The 4 properties that I believe are required to build great applications. If you think this is interesting and we're going in this direction, Neo4j is available for free in our cloud service Aura, so you can check that out, the QR code. We have a great Graph Academy where we teach people how to get up and running and build these types of applications. A few weeks ago, I don't know how many here are at startups, a few weeks ago we launched a startup program where we give away free credits and stuff like that, but maybe even more importantly, we're building a team of experts that help startups get up and running with Neo4j, right? So apply for that at neo4j.com/startup program. And that's it for me. Thank you very much.
Thanks, Emil, for the amazing presentation.
Thank you.
Awesome. Let's go now for a few follow-up questions, if you don't mind.
Yes.
Cool.
I have the coffee. That's the reward for getting through the representation. You get the coffee.
Very important, guys. All right, so you touched on memory and the AI layer. What do you think agentic memory would look like in the future?
Yeah, it's interesting, right? How many in here are using some kind of an agentic memory system today? Like, so probably a third or something like that. It's funny, right? Like, so this was more my objective observation, right? As a database guy, as a Neo4j guy, as a graph guy, there's a lot of people who independently come to the conclusion that agentic memory is intrinsically graph-oriented, right? So there's a couple of YC startups like Zep, right? Mem0, Cogni, right? Also, we mentioned MCP. Everyone in here knows what MCP is. Few people know that the initial launch of MCP actually shipped a tiny little agentic memory implementation. It's a toy. It's 300 lines of Python, right? But what is it? It's actually a graph, right? And so there's a lot of people who haven't talked to me who independently come to the conclusion that graph is a natural form factor for memory. And so that's one of the key reasons why we're really, really interested in it. And especially like being able to marry memory and the RAG corpus, like I just talked about, I think is so powerful.
Interesting. All right. To my next question then. From what you are seeing in the enterprise, do you think that more companies are building using AI to solve their internal problems, or you think they're buying AI solutions instead?
Like building application solutions rather than, buying application solutions rather than building. Yeah,
Yes.
Yeah, it's interesting. So obviously we've watched this very carefully. We sell primarily into the Global 2000, right? That's who we sell to. That's why we can do startup programs and give it away for free for startups, because we make a lot of money from Bank of America, kind of thing, right? And so we obviously have observed this very carefully. I think in the early days, let's call it 12 to 18 months ago, almost all of enterprise adoption of AI was in the form of applications. So in other words, they bought solutions, right? We've seen that change a lot, maybe experimentally a year ago, where people started trying to build a lot. But then in 2025, people really put it in production. So I think there's a massive surge of build. And then like the whole thing of whatever AI amplification of software engineering means that engineers are more productive. And then also the barriers of adoption for becoming a software engineer, where like being able to produce code is going down, right? So I think the way that it's trending right now and will continue is way more build than buy in terms of AI. At least that's what I'm hoping. Since look, they build on us, right? Like so, that's my hope. But I think that's where it's going.
And do you think that lowering the barriers for software engineering is the primary motive here, or do you think that there are other factors that are pushing that? Are they seeing better quality just by building, or maybe the products out there are not fully responding to what they're expecting from an AI product? So
I think they see the promise of higher quality, but I don't think it's realized yet. Right? If you think about a company like Klarna, who here knows about Klarna? Yeah, most people. So they just went public 2 weeks ago. Swedish origin fintech. the CEO there publicly tweeted about, wrote this super long form tweet saying, you know, we kicked out Salesforce, we kicked out Workday, and 1,200 other SaaS tools, thanks to this AI platform that we've built. And in that long form tweet, he was very clear that the key secret sauce was graphs and Neo4j. So they built this entire platform, kicked out everything, right? And when I talk to CIOs of Fortune 500 companies, I've never seen the amount of emotion against SaaS sprawl, not since the hate for Oracle. By the way, I like Oracle. I think Oracle is a good database. But man, have CIOs hated Oracle over the years, right? Now CIOs hate the SaaS sprawl that they see. Look, I run a small company. We're a 1,000-person company, right? Our software budget is massive. I have no idea what SaaS products we're buying, right? Imagine, you know, Verizon or like massive companies like that, right? And so I think there's a massive promise in doing the Klarna thing, of rationalizing your kind of software ecosystem, get software that is bespoke to you, and not get 100 features of which you use 4. Right? I think there's a lot of promise in that I see a lot of traction inside of the enterprise, but it's too early. It hasn't yet been realized.
One final question for you. So Neo4j, you mentioned it, is a European company, right? You're based out of Sweden. And but you also have a huge presence in the Bay Area. So how do you see innovation happening in the AI space? Where do you see it most? Do you see it in Europe?
Technically, we're actually an American company. We're incorporated in Delaware. We're headquartered in Silicon Valley, but I founded it in Sweden. All of our engineering is in Europe, primarily Sweden and London. Not a lot in Paris, but we are hiring, by the way. So if you find this kind of stuff interesting, please apply. And we talk internally about building an American company with a Swedish soul, trying to marry the best of both worlds. Probably going to end up in some 2x2 where we get the worst of both worlds, but we're trying hard to get the best of both worlds kind of thing, right? I think it's shifted a lot. When I moved to Silicon Valley, I moved there in 2011, and then I moved back before the pandemic, so I now live in Sweden. But when I moved there in 2011, really to build a company like us, you had to be in the Valley, right? Like developer, deep tech, infrastructure, there's just no other place. And you probably didn't have to, but I liken it to running uphill versus running downhill, right? You know, the center of gravity for everything was Silicon Valley, right? That in the early days of AI, it felt exactly the same. Like in 23, maybe early 2024, it felt exactly the same way. AI innovation wasn't even in Silicon Valley. It was like an 8-block radius in San Francisco, right? So it was right there. I think things are shifting really, really quickly. I love being here in Paris, like catering to a home crowd, but like, it's just been amazing to see what's going on here in Paris. Even Stockholm in Sweden is getting some real traction there with the kind of lovables of the world. Berlin, of course. London is a little bit slower than I would expect, but it's really starting to happen in Europe right now. If I were starting out today from scratch, right, it's not obvious to me that I would move to Silicon Valley.
Interesting. Well, that's it for me, Emil. Thank you so much.
Perfect. Thanks, everyone, for paying attention.
Let's give it up for Emil. All right. So up to our next speaker. So our next speaker leads engineering at Docker. Please join me in welcoming to the stage VP of Product Engineering at Docker, Tushar Jain.
Hey everyone, hope you're all having a good time. This is a great conference, by the way. Really glad to be here. All right, I hope everyone here will agree with me. I hope everyone here knows Docker. I'm going to assume you all do. And I hope you all agree that like the key thing Docker's done over the last 10 years is make it easy for all of us and all developers to adopt microservices and containers, bringing standards, easy tooling, and trust in the ecosystem with things like official images and hub. We now see a need to do the same for agents and tools. And so that's what I'm going to talk to you about today. A framing I like, and we like to think about this, is agents are the new microservices. The same way we moved from monoliths to microservices and needed containers, A similar shift is happening with agents. We're now going to move to agents calling each other. Containers are still the right paradigm, but we need to build on top of them. We need to build standardized packaging for agents that understand what agents are, what the dependencies are. We need trusted catalogs, and we need to make it easy for everyone to share and use these. So today I want to briefly talk to you about two things we're doing in this space. First, this is an early exploration we're doing, which is we think there should be standard packaging for agents. You can package them as containers, but it's not aware of what an agent is. Today, if you just package in a container, we don't know what tools they're using. If you share them and use them, you have the same problems you had earlier, which is like, what are my tools, what are my configs, how do I run them in any environment, what's the runtime I need? There should be something similar to a Docker file, like an agent file maybe. Like imagine a Docker agent, build, push, pull, run. So we're going to go do that, and we're exploring this and building this. And to get started here, to kickstart this, we've open sourced C Agent. That's the GitHub link. Please go check it out. It's an easy-to-use agent builder that makes it easy to build agents, but importantly, package them up as OCI artifacts and makes it easy for you to share them around via any OCI registry or hub. And so this is early exploration for us on how to package agents and share them. So we'd love for you all to go try it out and put any feedback, and we're going to work more here. And if you're interested in talking more about this, please do find us at a booth. OK, next, for agents to work well, everyone here has heard about MCP. We're all using MCP. But we think for developers to use this and make it easy, there are a few things needed. One, you need, same as everything else, you need good packaging. Packaging local MCP servers as containers is, we think, the right thing. You get security with it. You need easy discovery. And you need trust still. Like, how do you go find what is the right MCP server for the thing we're using? Like, what's the Docker official images version of MCP? Like, how do you know what's trusted here? And then you need security and easy tooling around this. Prevent rug pulls, prevent all other security threats. So to do this, with two things we've done that we'd love to talk to you about. First is our MCP catalog. You can go to hub.docker.com/MCP, and you'll see a catalog of MCP servers. Think of this as the Docker official images for MCP. They're trusted, verified MCP servers. We'll be adding to this. We'll have community servers. We'll have a way for you all to add, anyone to add images. But on top of that, we'll add a bunch of security. So prevent rug pulls, containerized local servers. We support remote ones too. But it's an easy, trusted way to get servers you need. And second, in Docker Desktop, we've added tooling to make it easy to use MCP servers. Because today you have to go configure each client using Cloud Desktop, Cloud Code, Gemini independently. We can make it easy to discover these, configure them once, use them easily, and add a bunch of trust on your laptop when you're doing it. So you're not doing just npm installs of random software with access to your whole machine, but containerized, secure. So I'm going to quickly show you a demo of that, and hopefully you can go try it out after that. All right. So bear with me as we do this demo. OK, so let's first orient ourselves. Hopefully it's legible. So if you go to Docker Desktop, you'll see MCP Toolkit there. Go check it out. Here's a catalog of servers. This will be growing. I can easily add them. I can connect them to clients. So let's do this. The setup here is, I've got some PM. They've been collecting feedback in Notion. I've got feedback from people here on Docker Desktop. What I'd like to do is have something consume this and go create issues for me in GitHub that I can go work on. So let's go do this. I think I need a GitHub client. So cool, let me just add that. And I've already configured this with OAuth, as you can see. And then let's go get a Notion one too. So let me go enable that. Cool. And I've already configured this with my secret here. It's all stored in secret management stuff. And I'm going to use Cloud Desktop. So I can just come here. You see a whole number of clients we support easily. You don't have to go manually edit config files. Let's just connect Claude here. So just do that, done. Great. Let's start up Claude. Let it come up. All right. So you can see here in tools, there's Docker and a whole bunch of tools there. Let's just do a quick test with this. What feedback do you see in, and what's the name of this page? In the Notion page. This will run for a second, and then I'll kick something off briefly here. The problem with these demos is hopefully Claude is fast. So you can see here it's gone, easily connected. I don't have to go muck with any config. Easy configuration, it just worked. And while that's running, I can just go do a little workflow here that I can automate that says, read from here and go create issues for me. And so what I've done, great, it's done stuff. It's getting more. I'm gonna start a new one so we can just try something new here. All right, so now I'm gonna say, go look at the feedback and categorize it and put it into GitHub. This will take a while to run, so I won't make you all wait for it. The key thing I want to show here is it was really easy for me. I don't have to go muck with any config files. I got official servers that I can trust. They're running containerized versions. They don't have access to everything they shouldn't. We have protection here for any rug pulls, etc. We'll be adding lots more security controls in here. And as a developer, I personally find this very easy to go use and run. And now I can start automating my workflows here. And now we want to take this further in the future to let you easily build agents using this tooling so you can automate all this stuff. And that's running. I won't wait for the whole thing to run. All right, I'm going to go back here. Cool. Here's some QR codes. Go try it out. Go try out MCP Toolkit. Hopefully you find it useful. Give us any feedback, please. And do go play with C-Agent and start building agents and seeing the packaging. And we'd love to see any feedback you have there. And over time, you should see from us coming out standardized packaging, hopefully an agent file, and more stuff for MCP. That's it. Thank you. Do this. Cool.
Let's give it up for Tushar. Thanks. All right. Up next is someone who's been at the heart of how developers build and collaborate for years. He's the Vice President of Developer Relations at GitHub, where he helped shape open source communities and has been involved with GitHub Copilot since the very beginning. Today, he's here to talk about the MCP protocol and share some hard-earned lessons from running one of the most widely used MCP servers at GitHub scale. Please give a warm welcome to Vice President of Developer Relations at GitHub, Martin Woodward.
Hey everybody, thanks for having me. It's good. It's always exciting when you see the thing you're about to talk about being demoed live on stage just before you get on stage. So thankfully the MCP server still works, so that was good. My name is Martin Woodward. I work at GitHub, and we're going to talk about our MCP server at GitHub. But actually, what I'm going to be talking about mostly is the MCP protocol and how you can get involved in the MCP community. We'll not be touching that much on the GitHub MCP server at all. It's mostly about the MCP protocol. Hopefully that's good. So, as you know, you might have heard of GitHub. You know, it's the home for the world's developers. But we've created GitHub Copilot in June 2021. And that kind of changed how we think and how a lot of people work with developer tools. It was a very exciting project to be on. I was lucky to be involved in the first version and have been involved ever since. As we've been doing that project, we've been learning a lot along the way. We've got now over 50 million users. We started by just doing autocomplete. So just, you know, because LLMs weren't that good yet. So we did autocomplete because it was only a little bit of code that needed correcting. And then as LLMs got better, we went into chat. And now we're at where we are in 2025, where the LLMs have got so good and can run longer times unsupervised that we're able to move to the world of the software engineering agent, which is where the industry is this year and where we've seen explosive growth across LLM usage for development. But you need to get data, you need to do all that sort of thing, and that's kind of where MCP has come into place, to be able to do things with your agent and be able to get data into your agent, as we just saw. But what I thought would be useful, first of all, would be to kind of, you know, with all these agents together and interoperating, how did we get here? How did we get to where we are today? So it's amazing to me. I'm old, very old now, and it's interesting to be here at the beginning of yet another epoch, yet another change of the way that we build things. So as I say, Copilot introduced in June 2021. we only got function calling in GPT in like June 2023. So that's less than, just over 2 years ago as we sit here in the room. So this is very, very fast. We then rapidly followed that with Copilot extensions, and that was basically a way for end users to be able to plug in to that whole function calling thing, and developers to be able to provide tools to Copilot specifically to be able to then talk to the rest of your development system. We're GitHub. We know that while we're at the center of your developer universe, you need to be able to talk to everything, otherwise there's no point having it there. So that's why we introduced extensions. Then later that year, Anthropic announced MCP. And the cool thing about MCP was that the tool discovery is more dynamic. You can tell the LLM what tools you have available, and you can give the LLM sufficient context for it to be able to do the tool calling, rather than the function calling, which was a lot more kind of API-based. We've got full support of MCP inside of Visual Studio Code, and then in April of this year, this year's been fat. It's been a long year already. So April, we did the local MCP server for GitHub, the official one. When Anthropic launched, they did a version of an MCP server that used our APIs, and then we worked with Anthropic, and we have our own, and made it open source, and everything's good. And then we also have now a remote MCP server. So if you don't want to install anything, as you saw in the demo from a colleague at Docker, you can just talk to a remote MCP server and everything works. So that's kind of the history, and it's moved very, very fast. But it's important to know that you're all here at the beginning of this new wave. And so things you might think, how does this work yet? It's because it's so early is why, a lot of times. As we've been building MCPs, we've learned a few lessons. The first lesson that we've learned, actually, is that everybody knows MCPs for tools. It's what made MCPs successful, and why people start using MCPs. It allows you to do things like create issues, send email, execute scripts, perform actions, as well as allow you to get data to add to the context of your prompt for your LLM. So that's the key values. Tools is at the center. But it's much more than just tool calling. If you just call tools, then you miss out on some of the other parts of the MCP protocol that allow you to call tools better, more efficiently. I did an update on the MCP protocol. These are the basic constructs in MCP. So we obviously have tools at the center on the server, but what you can do as a client, you can ask for resources from the server. So, if you're talking to GitHub, that's things like files, issues, like data that you need to be able to be part of your context. Or if you're talking to Notion, that's your Notion forms. If you're talking to a database, that might be database schema, that sort of thing. So the resources, you can separately access them as a client of an MCP server. We also have prompts, which is cool. Prompts are a bit like the stored procedures of the MCP world. You can ask an MCP server, hey, what good prompts do you have? And there's variable substitution in there that you can insert data. So if, can I have a prompt to do this thing, please? Can I have a prompt to do that? You can actually ask the server for some good prompts, and the LLM can do that, and it'll be great. Over on the client, the client can also provide a couple of things. One is sampling. So a client can allow the MCP server to send back, be able to do a lookup against the LLM that the client is using. So at GitHub, in GitHub Copilot, we allow the developer to pick whatever model that they want from whatever development environment they're in. And so it's essential for an MCP server like ours to be able to use what the customer wants their LLM to be. So if you want to use Claude Sonnet 4, great, we can do that. And now our MCP server can go to the client and say, hey, use the user's chosen LLM to do this bit of work for me. Or if you want to use Gemini, or if you want to use whatever models. So that's why that exists. And then finally, root is the ability to the client to specify where in the file system, where in the client server resources live and where the server can access. So you don't go accessing for things that you might need root level permissions, for example, to be able to see, or you stay within your sandbox. And then dynamic discovery, we kind of is part of the MCP protocol that people know. It discovers tools. Lastly is actually elicitation. That's very underused, as you'll see, but that allows the MCP server to tell the client, hey, I need more information about X. I need to make a decision. Can you ask a question? Do I do A or B? That usually means that goes to the client as a question. Do you want me to do A or B? Or it might be the LLM makes that decision for you, but you're asking the client for input at this point. And that helps prevent hallucinations. That helps prevent ungrounded work. If we look at the tools, it's great. And the reason why MCP was super successful is because it is such a pragmatic way of calling tools. But the problem that we have today is a lot of our examples with MCPs are just focused on the tools rather than the bits around the tools. And so unless we as a community do more work to get better at tool calling, nobody's going to be aware of what else is possible, which is one of the reasons I'm here, to try and help you see what else is possible and help you dig in, encourage you to dig in. I did a quick survey of all of the MCP clients on Monday. And of those clients, there's about 80 today, different client implementations of MCP. 79 of them know about tools, but if we look here, only 3 of them know about elicitation part of the protocol or have it implemented. So it's very, very early in terms of our implementation of the spec. The spec was only written in June, so it's nobody's fault, but it's still early days. If you are experimenting and want to, you're building an MCP server and you want to test out everything, actually, I would encourage, I'm not on the VS Code team, so they're a sort of sister team to my team at GitHub, but I would encourage you to give VS Code a try. It's the only client, that's the end client that implements everything in the MCP protocol and all the authentication specs. So try it there, and then that'll help you hopefully plug it in everywhere else. Right, so the first lesson that we learned once we started adding lots of tools is that actually tools are not the answer. Just like humans, the more choice you give to your LLM, the more likely it is to get confused. And the same is true with tools to LLMs. LangChain did some great research around the degradation in terms of performance of the LLM for coding, the more tools that it had access to. So you get overloaded, it can break down, and it can slow down the performance as well. Therefore, what we did initially, I have a very, very easy job because you are my end users, you're developers, you're technical. So it's easy for me to do things because I can ultimately just give you control. And you can decide which tools to switch on and off, and you like that as developers. Many people who are not building developer tools don't have that luxury, because if I went to a normal person when they were booking a flight or trying to do some insurance comparisons, the agent-to-agent protocols, and asked them to pick tools, they would, no, they're not going to, normal people don't want to do that. Developers like to do that. So we initially gave you all of the control in the client to be able to control which tools that you select. But what we obviously need to do is dynamic tool discovery. That's what's great about the MCP protocol, in that you can query the server to say which tools are available. But what's been added in the June version of the protocol is actually the ability for the server to say, okay, we've been having this conversation. I'm now going to add a new tool to you, LLM, that you can call, that it kind of unlocked at this point in the conversation, and it can broadcast the fact to the calling client that this tool is now available, and then it can broadcast this fact that this tool has gone away to the LLM as well. And by doing that, it reduces the amount of tools available to the calling model, at any one time to, again, minimize the amount of tools to increase the accuracy, to prevent confusion. So that's what dynamic discovery is good for. The next lesson that we learned, unfortunately, is installing MCPs is a pain. Nobody wants to do it. Trying to do cross-platform MCP installation is an absolute nightmare. Now, Docker we're just on. Docker is fantastic as a developer for getting a containerized MCP server, but that's fine for us as developers. That isn't going to work for end users, for normal people. So containerization is great, but only gets you so far. And if you look at the amount of commands you can use when you're defining your MCP server, there's everything here. Trying to get it to run on Linux, on Mac, on Windows, basically impossible to do reliably as a local MCP. Now, the other lesson that we learned, I did a quick grep of the logs for people calling our endpoints from MCP servers. Nobody upgrades a working local MCP installation ever. Once it works, I am not touching it until it stops working. Now, this protocol is changing so fast, our world is changing so fast, that's not sustainable for us, you know what I mean? If people are never going to upgrade. And because of the way that we do installation, like trying to do auto upgrade is basically impossible. So local, again, is great for development, is not going to work at scale once we start rolling these out to normal people. So remote MCP servers have been introduced, and this was kind of in the protocol from the very early days. MCP has always been a network protocol. And a remote MCP server is obviously installed remotely. It doesn't have any access to the client, like file system and things, without asking the client, and it's very easy to upgrade to scale. So as a service provider, remote MCP is great, and as an end user, it's fantastic too. But as a developer, there are some downsides, If I'm building an MCP server and I have to stand up a remote server first, it's hard. So local MCP has some great advantages to you as a developer when you're building MCP servers for speed of iteration and for experimentation. The critical thing that you need with remote MCP servers, we mentioned there, is good authentication, but we're going to touch on that in a second. Locally, you can rely on local secrets and the permissions of the local user. The trick that we did is we built both a local MCP server, and then we used that exact same logic hosted to be our remote MCP server. So our local server, fully open source, everybody can develop on it, anybody can add features, it's all good. We can, as an internal team, iterate very quickly, and then we can take that logic, host it remotely, and then we upgrade our remote server as well. And that then enables server-to-server scenarios. So you can go to github.com, talk to the GitHub MCP server, and manage that whole thing because there's a remote instance rather than having to rely on your local instance. The next lesson that we then had, once we did remote MCP servers, is password or PAT-based authentication is bad. It's an anti-pattern. You can very easily, managing those secrets is hard. They always become long-lived secrets, which is bad for security. Preventing them from being accessed by other MCP servers that have access to the file system is very, very complicated. There are lots of reasons why password-based PAT authentication is bad, which is why in June we actually added OAuth support to the MCP protocol. So now MCP supports proper tokenized security with short-lived tokens. It supports OICD Connect as well. So OAuth support is key, but not every client SDK has OAuth support yet. And we all have, if people here have built OAuth integrations, it can be, there's more pain there, there's more friction to go through, but it's necessary friction before you productionize something that's talking to MCPs. Local, you can get away with it fine, but once you go into production, you really need to be supporting OAuth. Okay, and then the final kind of lesson that we learned is your MCP is completely pointless until people can find it. You saw in the Docker example just now, going into a marketplace, finding MCPs that did what they needed and plugging them in. Without that discoverability, nobody can use your MCP server. So we need to make it easier for people to be able to find MCPs. So what we've done there is as a community, we've created an open source MCP registry. This just shipped like 2 weeks ago. There's a link there. Go and have a look. You basically have now the ability to use an API to publish details about your MCP server to the world as part of an open source, everybody shares a base repository of the MCP servers that are available. Now, I've been around, like I said, I'm old. I've been around through lots of different programming languages with package managers. I've been around with lots of different, like NPM and .NET and things like this. I've been around in different ecosystems. The thing that I'm very keen we prevent is creating like a single point of failure, a single monopoly of registries, because no one registry solves everybody's problems. There's a lot of trust involved in which MCPs you switch on and you enable. And so we need to be able to make it so people can have their own MCP registries and be able to distribute that load. GitHub now have an instance of an MCP server that goes and you can get like the GitHub catalog of MCPs. That adds additional data from the base catalog, such as how many stars it's got, how popular it is. So we can see Context 7's really popular. The GitHub one is obviously. Markdown, that's a cool plugin from Microsoft actually, which turns stuff into like doc files and things like that into Markdown so you can crawl them. It's cool, super popular. What we want to do is build an ecosystem, just like you saw with the Docker example just now, where we have a central registry where we can make MCPs discoverable, and then you have local registries. So Docker has a registry that you can go to when you're using stuff inside the Docker area. Your company probably should have a registry at some point that allows you to decide which ones you trust in your environment and all those sorts of things. And that discoverability is kind of the key to the next level to make MCP, the success it is. MCP has now become the API layer of AI. It's how it's going to work. I don't see anything else coming along here. There are complementary things like A2A for being able to talk between agents. But in terms of tool calling, being able to do things, MCP is the protocol we're going to be using. MCP is fully open. It's available for everybody to use and talk to. So I would encourage everybody to get involved. If you want to be part of this community, now is the time to influence the direction of what we're probably all going to be relying on for the next 20 years. So if you want to go to the MCP community site and get started, that's there. And then there is also a Discord as well that you can join in terms of being involved and being part of the community steering the future of MCP. Leave that briefly up for a second till I see the cameras go down. Great. One more second. There we go. Okay, so there was the lessons we learned very briefly. I'm around all day today if people want to talk more and chat a bit more. But what I want to do is encourage everybody to get involved in the MCP community. Let's build from here together. And now, on to questions. Thank you for your time.
Awesome. Thank you, Martin. All right, would you like to join me for a few follow-up
sure.
questions?
Oh, we're sitting down. I'm
cool.
This is cool.
Let's do it.
Yeah.
All right. Wow, so many lessons about MCP, right? And I actually loved when you mentioned that you dynamically pull the tools.
Yeah.
And you spoke about remote MCP and OAuth.
Yeah.
Where do you see the protocol going, or what do you see? Is there anything that you're actually like needing in the protocol at the moment? You feel like?
Yeah, I mean, the protocol as we did it, as it's done in June, is pretty complete now for what we know we need. I think the biggest thing is to get all the client implementation, so getting the SDKs to make it easy for developers to be able to use the full protocol, because you don't want to care about elicitation and dynamic discovery, and prompts and things. You just want to go to an API and say, call this in a good way, So the next bit of work is to kind of simplify access to the underlying protocol, I think, and then probably the discoverability in the registries is the next area.
Right, yeah, I totally feel you with discoverability.
Yeah.
I think like maybe agents should be smart enough to be able to go and find out about the right MCP server.
Yeah,
and just
that's totally why there's an API there, so that agents can autonomously do that. But as we've seen, the there are judgments to be made in terms of trust, because you're having a thing execute things on your behalf. So, and there's also value decisions as to, say you had 5 flight booking MCPs, which one of those do you call? And that logic as to which one you call is like critical business logic that you want to have control over. So, yeah, it's an interesting area. But I think now the fundamentals are probably in there in the protocol.
Awesome. You also mentioned that the MCP is new API layer.
Yeah.
So do you encourage everybody to get started with just turning their APIs into MCP servers? Is that the right idea to get started? Like if I start with an MCP server, what do you think?
Yeah, I think LLMs are ridiculously good at writing MCP servers. So the easiest thing is to, crack open VS Code, Copilot, crack open Claude Code, whatever you want to use, and get it to build you a quick MCP server that you can play with. I've just done, we did an MCP server that allows you to play a game of tic-tac-toe or, allows you to kind of interact. Doing that locally and being able to see how it's working just helps you kind of understand the base protocol. And then, yeah, sure, having a remote MCP endpoint for your business, it might make sense for a lot of people. I also think there's probably the need for some MCP servers for platform engineering to help us in how we build and deploy things inside of our organizations. If we can make it so that every developer from their development environment can say, give me a new development environment, please, add this database connection, like all those things where you need to go talk to a human or need to get into a ticket queue and wait. If you can automate some of those with MCPs inside your organization, that'll really speed up your development flow, I think.
Awesome. Yeah, you mentioned that you've been involved with the developer community for quite some years now. So when you meet new students who want to get into computer science, what do you tell them usually?
I'm looking. We've got a minute left, so yeah, I've got skin in this game because my son is a third year of a 4th year masters in computer science. I look after at GitHub. I look after our education programs as well globally. So millions of students worldwide. I firmly believe we need more computer science students tomorrow than we have today. The students that are coming out, we need to give them exposure to all these tools. So we give it to them for free so that them and their teachers can have exposure to using AI tools. But it's really interesting seeing that the teams, it gives them much more exposure into working with somebody else, i.e. the AI agents, than they would have typically coming out of an education program, which is encouraging to me. Typically with when you're a student, you basically come out thinking, I need to do everything myself, and group projects are painful. I never want to work in a team is kind of what you learn from your degree. And so, but when you're working with AI, you're getting used to analyzing the code that was created by another agent, seeing what works, seeing where it's gone wrong, and being able to critically fix things. And that's a skill as an engineer we need to just do every single day. So I'm actually pretty encouraged by what I'm seeing in the data of what's coming out. But we need more and more engineers, and so strongly encourage students to do that, but also strongly encourage companies to make sure that they're hiring new junior developers, and because nothing grows a senior engineer more than growing a junior developer.
So yeah, it's very interesting when you hear people saying that the junior developer is kind of dead. But
yeah, not at all. We need more than ever. But the impact that junior developer can have is a lot greater than it has been.
I think there's been never a better time in history to be a software developer.
Especially if you don't speak English as a first language as well. Because now the LLMs can explain code to you in your native language and things. That's huge. I take it for granted because I speak okay English, but but if you're learning computer programming, to have to learn English as well is horrible. So it's great we're improving that too.
Awesome. Thank you so much, Martin.
Good to meet you. Thanks for your time, everybody. Thanks.
Let's give it up for Martin. Thank you so much. All right. How are you guys feeling? Good? Ready for a break? Okay, so 11:30 is when you need to be back to this stage. So please, let's go for a quick break and back at 11:30. See you in a bit. Thank you.
Ladies and gentlemen, please join me in welcoming to the stage your MC for the AI Engineer Paris, Developer Experience Engineer, Ralph Chabry.
And we're back. Woo! You guys have enjoyed the expo? It's incredible, honestly. So have you enjoyed the expo? Yeah, I need some energy. I need some expo energy here on the main stage, please. Okay, all right. So coming right up, our next speaker has spent over a decade building infrastructure, and now he's building the new infrastructure for AI workloads. In his talk, he's going to talk about what happens after the GPU gold rush. Are agents going to need more compute, more storage, more network? We'll hear about that. And he's going to talk about diverse hardware as well. So please join me to welcoming to the stage my friend, CEO of Koyeb, Yann Léger.
All right, and we're back on stage. So this time I'm not going to speak about AI engineer Paris. I'm going to speak about what we actually do and how we see AI continuously redefining cloud infrastructure. My main job is to run a company called Koyeb. And as Ralph mentioned, I've spent the last 14 years in the space of infrastructure in general. So I've seen a bunch of evolution from the beginning of cloud infrastructure to now and this new wave with AI. So we're going to spend 20 minutes together looking a bit about the evolution and what is coming next with the agentic era. So the first thing I want to highlight is if you look a bit back, so 2 years ago, 2, 3 years ago with GenAI engineering, the main thing which popularized AI engineering is LLMs backed by GPUs. So typically ChatGPT and all this, the OpenAI models were LLMs running on GPU. So if you look at the early 2023 AI stack, 2.5 years ago, it was relatively simple in the sense that in terms of number of components, you used to have like an API, vector databases on one end, then you had a limited choice of models. So typically in early 2023, you had the GPT models from OpenAI, closed source, and you had a few open source models, so the Llama models from Meta and Stability AI. But Mistral wasn't even there, for instance, and it was running on GPUs with a Triton inference server, probably simply because even VLLM didn't exist, and we're speaking of only 2.5 years ago. But now AI engineering is also content engineering, VLMs, so models which include like image and vision capabilities, video models, vibe coding, a big trend of this year, MCP and agents. We see all of this as an infrastructure provider, and I want to dive a bit with you on what the future of AI infrastructure looks like, how we are trying to build for this agentic era, and what are the changes we see. So the agentic AI stack is way more sophisticated. I picked a set of technologies which we see in this new stack. So it goes from the front end, which is regularly vibe coded. So we have app.build, Manus or Lovable to vibe code your front end. Our team made an experiment on this, which you can see on the expo floor. We have APIs which might be in more diverse languages because you have more SDKs available. You have the agents, which are probably going to be written in Python still, but are different like components. And then even the historical databases have vector capabilities or capabilities for AI. Then you have MCP, and for the execution and the inference of the model, you have also more diversity. So AMD is a credible player now and can be used for specific models. So you might have an image model running, a video model running on a different kind of hardware, or LLMs running on an accelerator here, for instance, Tenstorrent, which is an upcoming provider of hardware trying to disrupt the NVIDIA market, the market of NVIDIA. And you might not even see any of this because you might also be operating on a higher level of the stack with the inference endpoints. So if you look at what it means in terms of hardware infrastructure and infrastructure to operate, now it's a mix of GPUs, CPUs, and accelerators. You have large training, which is still performed with GPUs, fine-tuning and small training, where you will probably still have GPUs, inference where you can have accelerators, and people are probably today starting to train with AMD GPUs. But inference is where you're going to see mostly AMD GPUs, and then agentic workloads, which are actually running on the good old CPUs. Now let's dive into agents. I want to actually start by defining what is an AI agent, how we see it. And because the definition of agent varies highly, so the simple definition, if you look it up, is it's going to be a software system that uses AI to pursue goals and complete tasks on behalf of users. They show reasoning, planning, and memory, and have a level of autonomy to make decisions, learn, and adapt. For us, there is a key question of what is important in this definition, what impacts infrastructure. So it's software system. At the end, it's still like Python or TypeScript or another language which is going to run on our servers. It's going to complete tasks, and they have a level of autonomy. And what it means technically is that the level of autonomy, you're going to run untrusted code in general, which is generated by a model which is non-deterministic. So anybody who ever worked in security should think about like the danger that it involves, and actually the requirements it involves. And the first requirement we see with agentic workloads is secure sandbox environments. So to make sure that this untrusted code is not dangerous to your production platform or environment. We see requirements in terms of performance because they still need to run fast. The agents are mostly ephemeral, so they run for a short period of time. Because there is a high volume, efficiency is a key topic, and the deployment speed is also a key topic that we see. Now, on the Koyeb side, we build a global serverless platform, and we use this for agents and inference. So we provide a diverse set of hardware to support all these use cases. And I'm going to briefly show you. I'm going to do a live demo if it goes well. And we're going to execute sandbox code using the Koyeb MCP server. Let's do it. All right. So we are going to use Claude with MCP connector here. So it's called Koyeb Sandbox. What it's going to do, technically, it's going to create a sandbox to execute our untrusted code. Today will be relatively safe. We'll execute some simple addition. But we'll see how what happens behind the scene. So here I have something which is pre-configured. If I have, okay, it should be fine. Which is pre-configured which should be pre-configured to run using the Koyeb Sandbox project. That's interesting. Okay. So we do have network here, And basically, okay, here we go. So I'm going to, it basically instructs the agent to create to use a Koyeb sandbox to execute untrusted code. So what we're going to do now is we're basically going to ask him to execute untrusted code. Can you please execute this untrusted code? And it's going to use our MCP server to create a sandbox. All right, so here we have the account technically where we run the MCP server already, and we're going to see sandbox being created behind the scene. So typically, we've done this demo with Claude. It could be done with anything else. So we also have a demo running with like Mistral to create the sandbox. Here we see that it's creating a sandbox called calculation sandbox, and that it's getting created behind the scene by the prompt. And so eventually, like, so this sandbox is healthy, and we are going to get the result here. Now, let's look at what's happening behind the scene and what it means. Right now, I just did this quickly. I went to Claude, I executed code, but coding agents are doing this automatically for you without you specifically asking to do it. So behind the scene, as a service provider, what we see is that agentic workload need to create thousands of secure sandboxes daily with sub-second starts. Like in this case, you want the result to be immediate. And this year is a year where we started seeing people coming to us telling us, hey, we need to deploy 10,000 containers a day because we have this agentic workloads which do this automatically. So if you use Lovable behind the scene, they are going to automatically do this for you, and they are going to create a container on an infrastructure provider like us. AtTopBuild, for instance, is doing this on Koyeb. One of the key questions for us from a technical standpoint is how fast can we boot an agent, and how many agents can we boot so that the experience for end users is seamless. The technical problem behind it is we deploy Docker containers, so they are stored in our registry, and we need to transform them in an agent executing your code. Behind the scene, our stack is actually leveraging virtualization to isolate the containers. So we use Cloud Hypervisor to run the container. We have, and on top of this, we have the container, the agents, and we might have, if it's an inference workload, we might have an inference engine like VLLM. And below, we're operating on bare metal machine. So when someone types a prompt like this, we need to get this all ready. The bottlenecks are multiples. So you have multiple bottlenecks, knowing that we're aiming to get sub-second like start. So if you were to create a bare metal server from scratch, it would take minutes. If you want to pull an image from a registry, it can take several seconds for small images. If it's a large model, it's going to be way longer. Your networking is going to be a problem because you have to converge between all your servers, so networking configuration. And then you also still have to execute the runtime of your agent. So typically, the Python runtime is going to take some time to start. In our case, one of the main bottleneck when we started seeing this increase of volumes was networking. Some people might think it's actually the virtualization engine. Firecracker has been quite popular lately, even so it's not totally new. But in practice, for us, the virtualization engine is not the bottleneck. In most cases, it's really the networking part, and it might even be something completely different in your system. So if you have a vault system, it might starting to take a lot of requests and just like be the bottleneck. We were able to mitigate most of this problem, so we preemptively start the machines, we cache the images on the hypervisors, and on the networking side, we made a lot of optimization to reduce the time. And we were the last part which we don't control is actually the agentic runtime, which we don't optimize the Python runtime ourselves. So this part is still like one of the components which might take time to start. We do have a mitigation though to be able to for this workload, to support this workload. And the mitigation is actually called scale to zero. That's how we mitigate most of the cold start. So let me back up a bit. If you're on the agentic workload, we have two key patterns. You have ephemeral sentences, which are going to be executed like during 1 minute. And if you are, for instance, using Lovable, it's going to create a web server at the end, which is going to run constantly. One of the challenge for these providers is a lot of people try it out, and then you have a huge fleet of services which are actually idling most of the time. And so, but someone might still be using them and they are looking to maintain it up and running. So to mitigate this problem of cost, we scale down to zero the workloads. If you've been in infrastructure in the past, one of the challenges when you scale to zero is how fast you can restart the server, because we completely shut down the VM. And so you will hit this time of startup. So we have two techniques like scale to zero and auto-scaling to increase efficiency. And we're able to reduce cold starts with snapshots. So what we do technically behind the scene is we do memory snapshots. So your agents, we're going to save the memory. We call this mechanism light sleep, and basically it reduces the cold start time from several seconds to 100, 200 milliseconds, which is not visible at all for end users. And so we end up being able to manage large fleets of machines without increasing your cost as an operator of such a technology. This is available now on CPU. This technology, we also have scale to zero on GPU. We're bringing the same principle of memory snapshotting to GPU too for this kind of workloads. If you want to know more, you're welcome to get started with our platform, and we have our engineering today on site. So please don't hesitate to ask them any question if you're curious about how it can be helpful. Thank you, everyone.
All right. Thanks, Yann. Would like
Thank
to join
you,
me
Rolf.
for a couple of questions?
Yeah, let's
All
do
right,
it.
Let's do this. I really enjoyed your intro yesterday, and I think we need to make sure that everybody understands that Koyeb is not an agency company, it's not an event company. It's actually an infrastructure company, right? So,
Yeah.
and you said that you were in the space for over 14 years, which is super impressive. So, can you touch on a little bit on what changed, in these 14 years building infrastructure, for cloud and now for AI?
Yeah, I mean that's I do love this question, but because we saw a bunch of changes while some stuff are consistent. For instance, what is funny is like if you look at our engineering technologies and our technical stack. We started 4 years ago with Firecracker as a virtualization technology. And then at some point, when we added support for GPUs, we went back to QEMU KVM because it was not supported with Firecracker, and QEMU KVM is a technology we were using 14 years ago
Yeah,
already.
it's been around for a while. Yeah.
So there are some things which are kind of consistent in terms of challenges. Then it moves like the scale at which we have to operate in terms of number of containers. It's like before you would have this scale, but with several customers. Now you have a single customer which is coming to you and bringing all these workloads, for instance. So some of the topics are consistent, like GPU. If you look back in 2017, we were already deploying GPUs.
Right.
So I was mentioning 2023, 2017 is what, like 8 years ago. So we were already deploying GPU. The difference is at the time, it was actually consumer-grade GPUs from NVIDIA, and they were only starting to create like data center-grade GPUs. So you have this stuff which are consistent and over time not changing, and you do have things which are completely new, like the diversity in accelerators. This is still maturing, and we believe it's going to take five more years at least to have a decent competition where NVIDIA start losing market share.
Is that what you were predicting? This is not financial advice, by the way. So, just saying.
Yeah, I mean, like, so we do believe that like the monopoly of NVIDIA is going to fall. We saw it in the past on CPUs. If you look back 10 years back, ARM was completely inexistent in the data center market. Intel was a dominant player. AMD was struggling on the data center market. Then AMD came to market, pushed back the market share of Intel, and now Intel is not in a great situation. So
yeah,
we do believe that the same is going to happen with GPU. Then the question is how fast.
Wow. Okay, so you're saying that we had the building blocks to build the AI infrastructure before, and now it's just the scale of it, the scale of the demand is just higher than what we used to see before.
The scale is completely different, and if you look back at like the slide I made on the AI stack, it looks again like a microservice stack. At the beginning, like 2.5 years ago, everyone was like just rack GPUs, and you have a set of new players who came to market by just providing GPUs.
Right.
Now, I think if you want to have a decent infrastructure, you need to have actually a set of services. It's not like as simple again. It's even if behind the model itself you have a lot of complexity, but it's also now several services that you need to coordinate again.
All right. Okay. So in your presentation, you touched on something that is really important to me, which is ephemeral environments, and you talked about secure sandboxes.
Yeah.
So do you see anything missing in those secure sandboxes for AI agents? What's the next step for them?
So on the agentic side, what we see a lot of development on actually higher level of the stack. So you need these primitives where the container starts fast. So you need to be able to execute containers because people want the flexibility to execute different runtimes.
Yep.
Then you need this isolation, which we're providing as a building block, and then people tend to look at SDKs, which don't need to be sophisticated, but basically where they can create quickly sandboxes. So we are looking into this, also helping like AI engineers create sandboxes without having to think really about the life cycle of the sandbox. Typically, that's what the MCP tools are doing in the demo I just made.
All right. Well, thanks, Yann.
Thanks you
for your time. Thanks for being here, and thanks for the talk. Let's give it up for Yann once again.
Thank you.
Thank you. All right. So I'm particularly excited for our next speaker. Coming up next is someone whose work has shaped the entire generative AI landscape. He's the co-founder of Black Forest Labs, the team behind the state-of-the-art model, Flux. Before that, he was a researcher at LMU Munich, NVIDIA, and Stability AI, where he co-invented latent diffusion that powers Stable Diffusion, Midjourney, and DALL-E. He was even named one of the Germany's top 40 under 40. Today, he's going to pull the curtain on Flux and tell us how it's built. So let's see about that. So please, join me in welcoming co-founder of Black Forest Labs, Andreas Blattmann.
So, hey everyone, thanks for having me today. Thanks, Ralph, for the nice intro. I want to talk today about our most advanced image model family, Flux, and I want to explain you the concepts you really need to understand how it works. I think Raul already has said a lot about me, so I'm Andy, I'm a co-founder of Black Forest Labs. We are the company behind the well-known Flux model family. And at BFL, we believe that visual media will be the central interface for human communication in the future. And our mission or our vision is to become the central infrastructure provider to power all the human communication through that visual media in the future, not only what cameras can do, but way beyond that. With that mission in mind, we've incorporated the company in April 2024 and launched it in August 2024. We've grown it since to 40 full-time employees that are distributed among 2 headquarters. Our main office is in Freiburg in Germany, actually in the Black Forest. And we also opened an office earlier this year in San Francisco. So we've launched our first model family, the Flux model family, at the day when we launched the company. And since then, we've mainly structured our releases in 3 tiers. I just want to share a bit light on those. So we have the Flux Pro models. Those are our best, most advanced, highest quality, and fastest models, and they are only available via the BFL API. They are just enterprise grade, and you can scale from 0 to massive volumes in, nearly instantly and without any infra hassle. As some of you might know, my co-founders and me, we've been the original developers behind Latent Diffusion and Stable Diffusion, so we've still very strong roots in the open source community, and that's why we also still are publishing openly available models. Also here in 2 tiers, we have the Flux Dev models that are open weights. These are available for everyone, downloadable on Hugging Face basically. They are self-hostable, so perfect for someone who wants to host a text-to-image model in their own infrastructure, and they are fully customizable, so you can fine-tune them to any extent, and in fact, they actually have by now a huge ecosystem attached to them of LoRa's, of fine-tunes, like a lot of stuff going on in the open source community. Super nice to see this. And finally, we have the fully open source Flux Schnell model. This is super fast and ultra lightweight, and it's basically the perfect entry point into the Flux ecosystem. And if you talk about the ecosystem, we can look at the model atlas on Hugging Face here, which basically shows all the ecosystem, meaning fine-tunes and stuff around the most important foundation models across domains. And guess which single model has the largest ecosystem attached to it? It's actually our Flux Dev model. So you see that we already shape, I think, the image generation space in the open source community very heavily. And as said, our vision is really to advance this further to become the central provider of images and videos that humans will communicate with in the future. All right, that much to the company. Let's now come to the core part of the talk. How to unify text-to-image generation and image editing. Why is that important? I think, first of all, image generation has made huge leaps in the past 5 years. We've been really at the forefront of this, I think. But image editing has, since very recently, not really kept up with this speed of advancement in image generation. I would argue that image editing is at least equally, if not more important than text-to-image generation, because it allows us to iterate over content multiple times and gradually refine it. I'll show you what that means in a second. And by that, it just gives us much more control over the output. whoever has professionally worked with images, I think, will totally understand what I mean here. So I think that's why it's a very interesting and important problem to solve. And with Flux Context that we released in June 2025, so earlier this year, we published the first diffusion model or flow matching model that combined text-to-image generation and editing. And that really unlocked new properties that we have not seen before, things like character consistency, style reference, local and global editing, everything within one model, available within seconds once you prompt it, so at really high speeds. And I think the top row of images here that I brought to you pretty much visualizes this. So we start here at the right part here with this image. We remove the object from her face. We keep the character then and transform it into a completely new scene. So in this case, this inner city. And in the rightmost example, we just change it to a winter scene. This is all possible within single seconds, and arguably whoever has used Photoshop before, this took just very long in Photoshop before we released this model, right? So here are a couple of more examples. Style transfer is really nice. So here at the left example, we just take the input image and transfer the style of it to a new prompt, basically, to new content. Or we can do fun things like text editing. Here we changed in the right example, Montreal to Freiburg, while keeping the font exactly the same. Importantly, Flux Context also solves a lot of interesting business problems. So we can actually get from an in-the-wild image of this skirt to a full-blown product shot within a couple of seconds. Or on the right side, we see that we can transform a simple sketch into a full-blown render also in a matter of seconds. So let's look a bit more at the pipeline and how image generation is different from image editing. Let's start with a classic image generation or text-to-image generation pipeline. We just use a prompt that describes a scene. We push it through the network, and we arrive at an image that hopefully follows that prompt. In this case, it does, I think. For image editing, it's quite a bit different. Here we start with an image, and instead of describing a whole scene that we want to generate, we only describe what I now call an instruction text prompt that actually tells the model how it should change the initial image. So here I say, convert this to a Lego scene, and we get the image of this church as a Lego scene. This all, again, in a matter of seconds. Combining these two aspects in a single model is super important because it just gets rid of very manual fine-tunes that we had to do before or complex workflows. So this is, again, text-to-image generation and text-based generative image editing combined in one model, and we don't need to fine-tune anymore or add workflows, which was the primary means to get to these editing capabilities before we released the model. All right, I think this gives a bit of a glimpse of the impact. I'll also show you a live demo of the model later. Now I really want to dive into how this model actually works. And in order to understand this, we have to look at an algorithm that's called latent flow matching, which is defined based on two concepts. It's latent and flow matching, and I want to share light on these two concepts because these are really important to understand how the model works. So let's start with latent. This comes from the algorithm latent generative modeling that me and my co-founders invented 5 years ago while we still were students at the university. And to start with, I just want to show you these two images. The left one is a JPEG image, which is an approximation of the right one, which is a PNG image. I would say these images look exactly the same. But if you look at the file size, we see something remarkable, I think. The JPEG image is actually 10 times, or like close to 10 times, or close to an order of magnitude, smaller than the PNG. So apparently, we can remove a lot of information without actually noticing it. And this is very interesting. And we can even visualize it a bit more differently if we plot the perceptual similarity of an approximation of an image, in the last example, the JPEG, and the original image, in the last example, the PNG. Against the file size, we get a plot that looks conceptually quite like this. So we have here on the left side that the perceptual similarity quickly increases with file size, but then stays very, very constant. You might ask, okay, what does this now have to do with generative modeling? This actually has to do a lot with generative modeling because it shows us that when we train the model on a perceptual signal, like an image, for that image to look real, you don't need to model all the high frequency, imperceptible details. So this part, this flat part of the curve, because here we don't increase the perceptual similarity anymore. This doesn't actually matter to our eye, and training on this would just be a great waste of compute and time. So we should not do this. And this is at the core of latent generative modeling. We really want to find a representation of an image that only contains those details in an image that actually matter to us. And this is how we do it. We train, well, we call this representation latent space. This is why the term latent generative modeling comes from, so generative modeling in the latent space. And this is how we train the pipeline. We train a so-called autoencoder to extract that latent space before we train the actual generative model. And it works like this. We start here on the left side with an input image, push this through a CNN encoder, extract that latent representation, where we will later train the generative model on, and then we apply an operation that's called regularization. This forces the model to discard information from this latent representation. It can be done either discrete or continuous. We mostly use continuous operations here, and then we push it again through a decoder to reconstruct the original image. And we train this model end to end, so we use a reconstruction loss that just minimizes the difference between the reconstructed and the input image. And importantly, we add this here on the top right, this discriminator loss. That is basically a prior to the human perception. This one takes care that the details that are contained in the image are actually only those that matter to our perception. And like this, we can arrive at this latent space that really only contains those details that matter to us. So this is the first part, and once we've done this, we train the generative algorithm to generate images from basically easy and tractable distributions. I come to this in the next slide. So, and this algorithm is called flow matching. Flow matching is a general family of algorithms that wants to find a vector field which is parameterized by a neural network that maps from a simple distribution. This is here visualized on the right side, so here, which is always the normal distribution, to a very complex and unknown distribution, which is our natural distribution of images. This is visualized here. So this is again in the latent space happening. I just explained this. We have the encoder to encode here, and we model everything in the latent space. So we want to learn a vector field that is parameterized by a neural network. And flow matching actually gives us a super simple algorithm to learn this. All we do is we couple each sample from our data distribution with a random sample from our normal distribution, so say this one, and we just repeat this for every sample in the data set. And like this, we can construct a artificial vector field. This is obviously, this looks really wrong because in a vector field, trajectories can never cross. Otherwise, it's by definition not a vector field. The interesting thing with flow matching is, if I just do this and train the model to approximate this horribly wrong vector field, I end up with a true vector field actually. So if I do this very often, the model in the end approximates the true vector field where we see that trajectories don't cross. This is the flow matching algorithm. And obviously, since we want to control the output based on text prompts, we condition our deep neural network always on those text prompts to be able to control it later. And once we sample the model, so say now we've learned this vector field, the network represents it. Once we sample from it, we just apply the vector field step by step in a numerical integration scheme. So we start with a sample from the easy and tractable distribution, from the normal distribution, and just apply a numerical integration scheme where each integration step is actually a forward pass of the neural network. And like this, in 50 steps in more or less, we arrive then from a sample from this easy distribution and a sample from the data distribution that we then again push through the decoder, and we arrive at a generated image in the end. So this is the flow matching algorithm combined with this latent generative modeling. All right, so this is how you can generate images based on text. But now how does this apply to Flux context? Because that also can do image editing, right? We do this with a very simple trick, I would say. I want to share a bit about the architecture of the model. So we train a general transformer model, which is the backbone of what we're doing for the Flux models. And we condition that. This is the same for image editing and text-to-image generation on a text prompt. This is here on the top left part here. But instead of only conditioning on one image that we want to generate, we condition on an additional image that is now the context image for the model. So we here have two images. We push them through the latent space, and in the latent space, we form a sequence of tokens. We have text tokens and we have image tokens for the two images, the one we want to generate and the one that is our context image. And we handle this token stream with a transformer architecture, which is composed of double stream blocks, where we have domain experts for the visual and the text tokens, and then classic transformer blocks that are just handling all the tokens similarly. And this is how we parameterize our network. And we can just change from text to image generation to image editing by using or removing this context image. So if you do a text to image generation, we just remove that image. So this is how it works, just a conditioning trick in the end. Last question I want to answer, how is it so fast? I think whoever knows the Flux models knows that they are pretty fast. What do I mean when I say fast? They are up to an order of magnitude faster than the competition. So we see the Flux models here on the left side of each plot, and this is both for image editing and image generation. So they are always on the left side, and say for image generation, we are 25 times faster than GPT-1 image, for instance. We are still for image editing up to 10 times faster than the slowest competitive model. So how is that possible? And the algorithm that powers this is called adversarial diffusion distillation. Here, the goal is to bring down the number of numerical integration steps. If you remember, I said these were 50 for trained models, or more or less 50 as a rule of thumb, down to as little as 4. And in order to do this, we do two things. We take a pre-trained flow matching model and initialize two neural networks from it. First, the teacher, you see it here on the bottom part of the plot, which is just this model itself. And then we initialize another new model, the student. The student should learn to generate images that are as good as the teacher images, but only in 4 steps. This is the goal. And here's how we do it. We start with an image again, encode it into the latent space, and then we use the student. This is visualized here on the top part. We use the student to basically generate this image or generate a generated image from it in 4 steps. Then we arrive here at the top right side at an image that in the beginning, when I start training this, is very blurry and looks very unrealistic. And I want to improve these images as much as possible. How do I do this? We use this generated image from the student, push it again through the encoder, and do the same generation procedure with a teacher. But here I use 50 steps and I arrive at a very faithful and nicely looking image. And we just train a distillation loss that compares the images of the student with the images of the teacher and pushes the student to follow the teacher distribution. This alone is not enough, which is why we add another loss on top of it, which is visualized in the bottom left part and initialized with a feature extractor called Dino v2. This is a discriminator loss, which is again a prior to human perception. This takes care that the images that the student creates are actually following or perceptually pleasantly looking for us humans. So again, they make really sharp edges for for the student images and make them realistically looking in the end. So this is super nice, and we can, with this algorithm, we can get down the number of numerical integration steps from 50 to 4, which is great, but it's very complicated. It's like 2 times encoding. So we see here in the top row, we see an encoding operation. Also in the bottom row, we see an encoding operation, and same 2 times decoding. So it's super tedious to train this and very computationally heavy. And this makes us arrive at the final algorithm that we actually use to train the Flux model. It's the latent adversarial diffusion distillation. You know now what latent generative modeling is. So I guess you know the motivation behind this. We just want to get rid of all the encoding and decoding, and we want to put the entire algorithm in the latent space. And this is what the latent adversarial diffusion distillation algorithm does. It just does exactly the same thing than the last algorithm, but it applies it completely in latent space. And for that, we change 2 things. We replace this dino, I go back once to see it, this kind of discriminator loss, this feature extractor, with the teacher itself. So we use the pre-trained model to as the prior to calculate this adversarial loss, and we throw away the distillation loss completely. By that, we can actually achieve much less compute efforts. Does this work? Yes. Much less compute efforts, and can speed up the algorithm a lot. So in a nutshell, latent adversarial diffusion distillation is just the adversarial diffusion distillation applied to the latent space. And by that, we can actually bring down the number of integration steps from 50 to 4, which is again this order of magnitude speed up that we've seen in the plots. So here we get a 12.5 times speed up. All right, now you know why it's so fast. And as a final, I think, thing that I want to show you, I have brought a short demo to you to actually see how the model works. So let's maybe use this image. Here we have an image of my favorite football club, the SC Freiburg, which is the local football club in Freiburg. And we can now just play around with this motif. So we say, put this logo onto a t-shirt. Oops. All right. Here we go. Hope internet is okay. Yes. Cool. Then we wait for a couple of seconds. And what we get is live demo. Nice, okay. Now we're hot. I think now it should be faster. This was too slow for Flux normally. So now we get this nice picture of the logo onto an image. The nice thing now is I can use this image and iterate over it. This is why I think editing is super exciting. So now I can say, okay, this logo is too large. Make the logo smaller and put it on the top right part of the t-shirt. Again, we submit here. And here's what I get. Again, 4 images, and I can just go on like this. Let's make the t-shirt red. And I think as the next thing, I want to do something more challenging. Let's put this t-shirt onto a human and transform them into the wild, because so far we've done like somewhat local image edits. Let's do something more global. Oops. Oh, in the park. All right. I'm now generating 2 examples. I don't know what's happening here. Okay, par also model could infer what I wanted to do. That's great. So nice. Here also good. Let's use her. And one final edit maybe. So this was a global transformation, which is nice. And now let's, as an example of style transfer, make this a watercolor painting. As the final one. Come on, last one. Ah, nice. Cool. And here we go. Now we could print it out and place it on I don't know, take it at home, whatever. No, I think the general thing is coming across. It's very powerful, very flexible, and I think this was it with this demo. I want to say thank you. We are hiring. Come visit our booth. We're just right next to the main stage here. We have a lot of openings, so if you're interested in what we're doing, please apply. Or visit our playground. This is where I basically just demonstrated the model. Thank you so much, and have a great conference.
What a great presentation. Thank you, Andy.
Thanks.
Would you like to join me for a couple of questions?
Yeah, absolutely.
And by the way, for Zuckerberg, this is how we do a demo. just saying.
Thank you. This was live.
All right, please have a seat. I have to say I'm blown away to see how fast the Flux models are. It's incredible. If you've who tried the Flux before? Wow, yeah. So
nice.
Everybody has noticed like how fast it is. But how much faster could we make it actually? So do you have a theoretical speed that you think we can reach?
I think once we reach larger models, we can actually get to one-step generation. I think that is really the goal. Flow matching models, diffusion models, they came from this kind of, what I said, numerical integration scheme or sampling process that just takes a lot of steps. And I think our goal is to really get down to one step, like our Flux Schnell model, for instance, does 4 steps. And I think once we get to larger models, we can actually go down to one step. And sure, I think the challenge or the goal is in the end real-time generation. And I think that is very feasible, getting better hardware, getting better algorithms, getting better optimization procedures. Like on Blackwell chips, we can do less precision, so we can do FP4 quantizations for the models. And I think we will definitely get to real-time generation with flow matching models, yes.
Wow, so you're saying by having bigger models, we're going to make them faster? So it's
a bigger model is effectively can represent a more complex transformation. In the end, like what I showed also, this vector field or this approximating this vector field is just effectively a mapping from an input to an output. And the more complex your model gets, or the more parameters I add, the more expressible these functions are. So I can model way more complicated mappings. And that allows me to just do less steps, because if I can look at it from a linearization perspective. Let's say I have a curve, and I want to approximate with linear parts, right? The more steps I make for this approximation, or with the linear pieces, the more steps I make, the better my approximation gets. And making a more complex model can get you can make the function you're learning more nonlinear, so you can actually also add things like curvature or something into what you're modeling in one part, and by that you can model more complex curves in less steps in that way.
Wow. Okay. And do you think that in the future, people like me who like to use Flux for image editing will just drop Photoshop altogether and just be editing using these models?
I don't know how you will be using these models. They actually getting integrated into Photoshop soon. So
wow, breaking news.
I think, yeah, how you will certainly use them for image editing. Where you will use them, I cannot yet say. But I guess BFL will also make a good proposal for using the models on our platform soon.
I see. Okay, so it's gonna just make like these tools a lot better.
Yes, and I'm 100% sure that these models will be the backbone for all the image editing that we will see in the future, yes.
Wow, incredible. Okay, so yeah, you touched on the different models that you guys offer, Pro, Dev, and Chanel, and so some of them are open weight. But how do you balance your focus between, building for open source, but also like focusing on the state of the art at the same time?
Yeah, I think we've just seen it as a very nice value proposition to structure it, like having state-of-the-art models in our API. These are just the best models for people who really want to get very fast results and don't want to deal with things like customization and fine-tuning, because to be fair, that's not everyone's business and not everyone's interested in that. So I think that's always good for people who want to get to the most powerful models in as little time as possible. But then you have this huge customization need that a lot of real-world applications have. Like when I'm building a face app or something, face editing app, say, I need a crucial amount of fine-tuning to just get very good at this very specific problem. And for this, open weights models are perfect because everyone can use them, everyone can customize them, or can get help with customization, but they can tailor them to their specific use case. And I think this need for customization goes very well with an open source approach, because effectively the whole community can work for you. You can just use all the insights that the open research community got from investigated in the past, right? And by that, this gives you just a huge tool stack that you, as someone who wants to customize the model, can get when they just build on our Flux platform. So I think we see this as a very complementary kind of approach that we are definitely seeing also for future releases.
Absolutely, yeah. So for most people, they're gonna just go to state-of-the-art model. But for people who have specific problems, those open weight and open source solutions might help them to
absolutely. And
answer their problems.
I cannot predict how this will continue in the future. I would not say that most people are going to closed models. I think it's just a distribution, and I see this as a kind of constantly evolving and changing distribution. So we might end up in a future where everyone uses open models or everyone uses closed models. I don't know, but I think from what we see right now, playing on both fields is very important to us, and we just love to see also what people are doing with our models. That's why we also, from a, I think, personal standpoint, cannot stop working on open models.
All right, awesome. That was my final question, Andy. Thank you so much for this presentation.
Thanks, Rolf.
Thank you.
Thanks.
Let's give it up for Andy.
Thank you.
All right. So, I can walk you out on the stage. All right, so 2 p.m. is when we need to be back here for our next talk. Okay, so and now we can wrap it up and go for lunch, and please enjoy, and see you at 2 p.m. Thank you.
Ladies and gentlemen, please join me in welcoming to the stage your MC for the AI Engineer Paris, Developer Experience Engineer, Ralph Chabry.
I always dreamt to do that. My God, the timing was perfect. Hello, everybody. How's it going? Great? I had so much fun this morning. So we had Docker, Neo4j, we had Black Forest Labs. And you know what? The fun is not over. Because our next speakers, yeah, they're going to be so good. And our next speaker has actually nearly a decade at DeepMind, where he was working in super cool projects like AlphaGo, AlphaFold, AlphaStar, and he worked also in Chinchilla, Retro, Gemma, and Gemini. But now, he co-founded and he's a CTO of the H company. So please, without further ado, join me in welcoming into the stage Laurent Sifre, co-founder and CTO at the H company.
Hello everyone, thanks Raouf for the intro. I'm Laurent Sifre, I'm a CTO and co-founder at H, and today I'm going to talk to you a little bit about our work, and really our work, literally like what it is. So me, I like to start the day, and I say to myself, I'm going to do one thing very well, so I'm going to do this slide deck. And then I'm going to open my email. I can see I have 289 emails, and I'm kind of a zero inbox person, so it really disturbs me quite a lot. And then I open my pro email, and I have 1,000 emails. And then I'm going to open my calendar, and then I'm going to open like a bunch of stuff. And like I think we're going to do a lot of micro tasks throughout the days. And this is my desktop, what it looks like. I just put everything in it. I think it's simpler. And then eventually I just create a new folder, old, and I put everything in it. And old is already taken, so I have to name it old 4, for example. And then, so there has to be a better way. And this is what we are trying to do at H. We're trying to build something at the intersection of agentic, UI automation, and also models. So agentic is basically anything that has to do with autonomy, decision-making, planning. UI automation is like how do you deal with software, but through the user interface. So it can be RPA or task execution. And model, we think model is important because, yeah, you can build on big models, generalist models, and I will say more about that, but we think it's massively inefficient, and we can do a lot better with a specialized model. So really what we are building at H, we are building computer user agents, so agents that can control a computer the same way a human would, so through the graphical user interface. So basically, you take a screenshot and some context, you pass that to the agent, and the agent outputs actions, but in the same action space as you would, like mouse clicks, scrolls, keystrokes. And the thesis for that is that right now, agent is a big word. You have many agentic companies. A lot of that is really RAG or tool call, MCP, APIs, and so on. So plugging it, LLM, interfacing the LLM with like strongly typed tools. But we think, it's not going to work for the long tails of tasks that I showed at the beginning. Not all software will have APIs, MCPs soon, and I think there are two reasons for that. One is inertia, especially in big enterprise world. Things are slow, and then there are more adversarial reasons for that, like business model. I think there are a lot of legacy software that have incentives so that this doesn't happen. Because they sell by the license, by the seat. So if with one license you can do more because you have an agent talking to the license, then they kind of lose money. So they have strong incentives to make that transition slower. And since sometimes they have monopolies, it's going to take a while to happen, this transition to agent doing a lot more in the enterprise. There are also more positive reasons, like there's actually a lot of intelligence that has been put into making the API, making the UI. I mean, the UI, it's like an effective way to present the information, and yeah, maybe like you can already use that context that has been built by many developers as the context for your LLM, and also if you want to assist humans. It's good if you work in the same action space as they do, so that they can show to the agent how they work, what they do, and the agent can show to them and automate. So there is already RPA where you can automate robotic process automation. So you can automate things through UI, through scripts, and so on. But it's very heavy to deploy. It's brittle, so if exactly the workflow changes a little bit, or if there is ambiguity, it's not going to work. So I think those are the reasons why we need and why we are building computer use agent. So concretely, I can show you maybe an example. So example is a task. Here it's like, okay, we want to go to Google Flight. We want to find a one-way business class flight from Buenos Aires to Amsterdam on January 10, and we want the details of the shortest flight. So there are a lot of kind of like weak constraints in this, and let's see, what an agent is doing. So yeah, if you can please maybe enlarge the, so we can see. So what happens is that you have basically the software. So here it's a web browser where we're going to navigate on Google Flight, and then the agent is going to take actions. So and every time we see the action, so here it's like clicking on the departure. Now it's writing the provenance Buenos Aires. And yeah, so maybe I can speed it up a little bit. Let's put 2x. Yeah, so the agent doesn't really know how the website works, how if you click on something, what's going to happen. It's really adapting in real time. Here, it's and every step we can see. Basically, it outputs three things. Some notes of what happened, what it thinks happened on the previous steps, some thoughts, so what it wants to do now. So now it wants to select one way, and then the action is click on the drop down for round trip, because it wants to set one way. Okay, so So yeah, and now we are coming to the departure. So departure is really hard because you have to navigate through a calendar. Every calendar on every website is different. And here we want January, so we need to click several times on the next month until we finally see January, and then we can click on 10. And if you want to script that in RPA, it's like a lot of work to explain the loop and all of that. So now it's selecting the class, web search. So now it's going to search. It's going to see the flights. It's going to expand. So it found the shortest one. It's expanding, and yeah. So you can do that with RPA, but it would be a lot of work. And here is just one prompt basically. And yeah. So this is our agent Surfer H. Okay. How do I? Okay. Maybe you can lower the screen, please. And the agent, the way it works, so you have the task. That's the prompt I showed at the beginning. And then you have the memory of the agent. And the memory, there are a few things in it. There's the task, the thoughts, the actions, the notes, and the previous screenshots. All of that goes through a policy model. So it's a VLM, a visual language model. So like it can be GPT-5 or Sonnet or model. And then it outputs actions, and we have a few actions. We have like refresh, go to, we have scroll, wait, and write and click. So the agent can write some text onto some element, or it can click on some element. And then we have a localizer model. So when you use an action that has a element target, there is a second call to a model to output the coordinates of that element, and that's the localizer. And finally, when we produce the final answer, we have another call to a validator model, and which validates if the task has been correctly executed or not. And if it has been, we just return the answer, or we incorporate the feedback into the memory and we continue. And every time the action is executed in the browser. And for that, as I said, we can use any model, but we can also use our own model that we developed that comes in. So those are our Holo models that we open sourced. They are really state of the art on this task of localization that is given. So I'm going to talk more about this later, but yeah, I think one question is why would you use a specialized model? This is 2025, so everyone is just prompting a big model and put your API key and just ship the product. That's what everyone does nowadays. So why bother and why try to do another model that does something? And the reason is really efficiency. And if you look at efficiency, let's take an example. Let's take chess, for example. And chess, you have GPT-5 or Grok that can play chess very well, like 1,600 ELO. It's probably like stronger than most people in this room, stronger than me. So it's quite remarkable that such a big model can play at this level without having be specialized to do it. But if you compare this to a specialized agent and model, like for example AlphaZero it plays at 3,600 ELO, so 2,000 ELO more. So that means GPT-5 is going to win one game out of every 100,000. And it's also a lot bigger. It's like 1 trillion parameter compared to 20 million parameters. This runs on like maybe a big pod of GB 200, $1 million supercomputer. And that one can basically run on a cheap gaming laptop. So all in all, GPT-5 can play chess, but it's like maybe 5 billion times less efficient than AlphaZero at it, or 100 million times less cost effective. So yeah, you have many orders of magnitude, and it really doesn't make sense, economically to play chess with GPT-5. And so that's what we are trying to do here for computer use agents. We are trying to basically move the Pareto front of performance of the agent. So this is Web Voyager. So Web Voyager is a benchmark. Basically, the task that I showed at the beginning comes from this benchmark. And so you have 600 tasks, and we measure success rate. And that is basically the success rate of the agent when you use different models. When you use GPT-4o, when you use GPT-4.1, when you do, 4.1 is here. And this is when you use our model that has been specialized for this. And we have currently a modest 5x cost effectiveness factor, but we are aiming at something closer to 5 billion, hopefully. This is the task I described about localization. So given a screenshot and an intent, here the intent is click on departure date input. You want the model to predict the coordinates. And that's what we worked a lot on. And for this particular task, we also have measured performance against the size of models. And here, it's not just us being better, but it's also, I think what's interesting is that you have this, what I call the specialization frontier, where basically every model below, they are generalist models. So here we have Qwen, we have Sonnet, we have actually maybe GPT much below on this particular task. And then here, these are specialized models. And so all of these models, they have been trained specifically for that. These are UI venues from Ant Group. They have a big team working just on that. This is UiTAR from ByteDance, also a big team working just on this problem. And this is our latest release from 2 weeks ago, Holo 1.5. So yeah, I think we're going to see a lot of these Pareto plots where specialized model really shine, and people start to move away from generalists because they find it's not very effective. This is how we trained Holo. We initialized the model with Qwen 2.5 VL, which is probably the state of the art in terms of open source VLM. So visual language models, we need to give it a screenshot, so it needs to be a VLM. We start from that, and then we do a little bit of fine-tuning on a mixture consisting of UI localization examples. So we've scrapped many different softwares and websites to get screenshot intent coordinates. We have other auxiliary tasks that we think are interesting, like question answering on tables, on UI. And then we have a lot of data that consists in execution of our agent on many synthetic tasks. So we have actually expanded this Web Voyager to something like 100,000 synthetic tasks on which we've run the agent, and we collected the successful trajectories, and we are training on the successful trajectories for web, for Android. And so that's the phase one, supervised fine-tuning. And then we do a little bit of GRPO, which is reinforcement learning. And for now, we are training the model to be successful, to optimize end-to-end for being successful at this task, not really reproducing the training data. And right now we are doing it on UI localization tasks, but we hope to expand to many more tasks in the future. So why open? We could also keep the model to ourselves. And these are, I think, all of the reasons why we want to do open weights models. I think for the customer, it builds trust. They know what's in the agent, and we are a startup, so they don't want to be fully reliant on us. If we give them the model, they know they can run it if we go under. It's a good conversation starter. People know, maybe they've seen the the model or the benchmark. So it's a good conversation starter, and they can try it before they buy it. I think it's good for the brand because like you don't have to trust me. You can download the weights and run the evaluation. So it's verifiable performance. For the tech also as a consumer. So when we build open source open weights, we also start from CoinVL in our case. So and we use existing training pipelines, maybe TRL from Hugging Face, maybe we can use also inference like VLLM. Like all of the stack is basically already done. And we don't have to reinvent the wheel. We can just focus on where we add value. And then for the employee, I think it's a good drive as well. They get visibility along the way. It can be a long web for a startup to be successful, but this gives them intermediate milestone and visibility, and it helps with retention and attractivity. So I think all in all, it's a good deal for everyone. What is next for us in terms of research? We want to extend to. We've done the web. We want to extend to desktop and mobile. We want to generalize. So before we trained on Web Voyager, we evaluated on Web Voyager, and because it's reinforcement learning, it's kind of okay to train on the test set, but really it's not. So now we are moving away from that, and we are training on this big. Only on this big synthetic task mixture that I described. We want to annotate, use like more humans in the loop. Sometimes the agent is really stuck, and you need to just show it what to do. So we are building tools for that. And then reinforcement, so do more reinforcement learning to optimize end-to-end for the task execution success. So multi-turn and so on. And then in terms of platform, we are the stuff I showed at the beginning, the demo, we're gonna make it public soon. So that's the Surfer showcase. We're gonna have a portal where you can go and create an account. You have your API key. You can launch the agent. You can do inference of the model. So that's coming very soon. And so with this. I thank you for your attention. I'll leave you with this quote, which is, why we think it's important to, assist more some kind of low-level tasks. And thank you.
Thank you, Laurent. Would you like to join me for a few questions?
Yeah.
Thank you so much. All right. Please have a seat. Okay. Wow. What a great presentation. I really enjoyed it. Actually, I wrote so many questions, but I'm gonna try to keep it short. So I really like when you highlighted the limitations of API and MCP, and you spoke about the contrast with computer using agents. I was just wondering, what's the biggest challenge, in your opinion, in building computer using agents?
So I think there are many challenges in terms of deployment. There are many questions like, do you run it locally? Do you run it on a virtual machine? What are the credentials? It's a big question. Yeah, we book a flight, but then what's next? Like, are we logged in? Are we gonna just have the, credit card number in the prompt? Probably not a great idea. So yeah, I think many questions around roles and permissions, and I think it's a great opportunity because it's already done in humans interface, and we can reuse some of that.
Yeah. So if an agent needs to act on the behalf of a human, like what kind of data they can have access to, etc. What kind of permissions are we allowing them to have, pretty much?
Yeah. So it's really dependent on deployment, and we are. Getting starting on the go-to-market side and so on, but yeah, I think either it takes control of your laptop and you have your credentials there, but then maybe it needs to confirmation and so on to send you confirmation before it pass an order or send an email. But yeah.
Yeah, I would like that too, if I'm informed. You spoke of go-to-market strategy. So can you tell us a little bit more about the business model that the Age company is actually having for this?
Yeah, so I think we're gonna have the Surfer showcase, but I don't think it's gonna be something you can pay for. You can try it, but if you want to, we don't want to basically build a per token business model. We think it's a kind of a race to the bottom. So we try to do this forward deployed engineer model, and we have Gauthier, our CEO, who comes from Palantir, and he's been very successful at doing this in his previous role. And we'll try to charge by the value and like how much more can you do, and we take a fraction of that compared to how many tokens. Like OpenAI is like $2 per million tokens. How much we're not gonna make money like that, I think. So yeah.
Yeah, it's quite hard to actually understand how much tokens or how many tokens does a computer as an agent needs, right? So that makes sense to me. Well, this is it for me. Thank you so much, Laurent.
Thank you.
Let's give it up for Laurent. Thank you so much. All right. So we're ready for our next speaker. This is going to be a speed run, but I think it's going to be exciting. So our next speaker calls himself a technological humanist. He's built systems for NASA, brought medical informatics to Zambia, and today at Neo4j, he's helping democratizing graph databases. His motto, everything is connected. So he's here to show us how to generate data and how generating data can be fun. So please join me in welcoming to the stage Generative AI Lead for Developer Relations at Neo4j, Andreas Kollegger.
Thank you for that introduction. Hello, everybody. Hello, Paris. So we've all probably done a little bit of vibe coding over the last year or so. I work at a database company, so I think a lot about, well, can you do vibe coding with data? Can you vibe with data? So this is my talk. This is the snack version of a fuller version of what I've got that I'll share later. But it's all about, and actually I love the previous talk, the idea that as soon as you go down the route of making any kind of agents, you run into all kinds of challenges that lead you down to making a multi-agent system. And you do a multi-agent system for a couple of reasons. You do that because the agents have got too many responsibilities, they get confused, they have context rot that happens, semantic drift that happens. So you break down the problem to make it simpler and have more agents that are focused on different parts of the problem. Along the way, because you've got multiple agents, you have the opportunity to use specialized models. The way that we saw in the previous talk, specialized models outperform general models in all tasks. So you have the opportunity, as soon as you break things up, to have models that do just one part of a puzzle. Okay, that's the quick setup. So I've been building a multi-agent system to actually vibe with data to help you build a knowledge graph, because I work for a graph database company. And this starts with top-level agent that interacts with the user and like helps figure out what the user wants to get done. But then there's 3 specialized channels here for either taking in structured data, unstructured data, and then once you've built a graph, retrieving information out of that, what's called graph rag from the graph perspective. So I'm going to take you through a speed run of what this looks like in action. I have a longer talk about like, the details of how you implement this. All the code is open source. I'm happy to share that with you guys as well. Okay, so here's the speed run in video form. Imagine you want to build a bill of materials graph. You don't know how to do that. So you turn to this agent and say, hey, I would like to create a bill of materials graph. Send that off. The first job of the agent is to figure out, what do you really mean? What are you trying to get done? It goes through a bit of bouncing around here, like figuring out which agent should pick up this whole thread, and realizes, okay, I don't quite understand what you're trying to get done here. Let me ask some clarifying questions. So to ask, tell me more about what you're trying to do with the knowledge graph. And I tell it, okay, great. I want to trace from the products all the way through the bill of materials, all the way down to the suppliers, so I can do root cause analysis for like product issues that are reported, like on a website review or something. Okay, human in the loop is important to me. So after the agent decides it thinks it understands what I just said, it says, this is what I heard you say. Was that correct? I approve it, and then it moves on to the next stage. And the next step, having understood what I'm trying to get done, it goes off to find what data is available that might satisfy creating that kind of a graph. It has tools available to it to look through the file system. For all the files that are available, it can kind of grep through those and find the content of the files. And then here it makes a recommendation about, here's the files that I just found, some product files, some assembly files, and also some suppliers. It presents that to me again for approval. I said, sure, that looks great. It goes on to the next agent. Now we know the user's intent, we know the data available. The third agent's job is just to focus on, given the data and the user's goal, what would the data model look like? So it goes off and does some analysis on that. And the outcome of the analysis is that it comes up with a proposal for what the graph could look like. And again, it's just a proposal. It doesn't actually do anything yet. Shows that to me. I can go ahead and look through it and see that looks correct. It looks like it covers all the kind of data that I'd like to have inside of the graph. And here I'm carefully scrolling through, making sure all the nodes are there, that the nodes are connected to each other in a good way. I've got a good connected graph. And here again, I'm just going to go ahead and approve that part of the workflow. With that approved, we can finally transfer over to the agents that's going to go ahead and build the graph. And the building part of it, and this is where the specialized agents really would shine, specialized both agents and models, is that if you go from just ideation with the user, you kind of maybe want OpenAI or generalist model for that. As soon as you go down to a specialized task, having specialized models would be amazing. And here we've gone through all the way, pulling in those data files, creating the graph, and it's even recommended some queries that I might be able to run there inside of the interface. Now, instead of dealing with the interface, I'm going to pop over to the database side to see what the data actually looks like. And here I've done a match looking for the products that are inside of the graph that was just created. This particular product is the Stockholm, I forget if it's a table or a chair, but that chair is made out of some assembly, some different pieces, and those pieces have some parts, and those parts come from suppliers. All of that was created on the fly by this multi-agent system. That is my speed run. If you'd love to hear the long view, come talk to me afterwards. I've got about 10 seconds left, so I can't take any questions. Thank you.
Thank you. Thank you, Andreas. Awesome. So, our next speaker leads a developer experience at community at Hugging Face, where he's been championing open source, audio, and on-device machine learning. He's here to walk us through the state of open source LLMs in 2025. Please join me in welcoming to the stage Head of Developer Experience and Community at Hugging Face, VB.
Hello, AI engineers. It's nice to be here. And thank you so much for tuning in for the talk. In the next 20 to 25 minutes or so, I'll present a report on the current state of open LLMs in 2025. And hopefully you'll be inspired to try them out by the end of the day or by the end of the talk. Let's see. So when we talk about open LLMs, like one of the first questions that pops to the mind is like, how do they stack up against the likes of GPT-5, the likes of Claude Sonnet, and so on and so forth. Thanks for us, there is an evaluation service, or rather a company, which has made it its mission to benchmark closed as well as open models against a standard set of evaluations. What you see on the screen is the average performance of recent LLMs on a bouquet of evals, ranging from math, coding, scientific rigor, and so on and so forth. The black bars that you see are proprietary models, and the blue bars that you see are open models. And what you can see right now on the screen is that in the top 10, there are pretty sizable amount of open models. So I can see 3 or 4 here. And if you look at it in absolute scores, the open models are actually quite close to the closed models as well. You can see that GPT-5 high currently, with like reasoning effort high, is at 67 absolute score, whilst GPT-OSS, another open model from OpenAI, is at 58. And there is a small caveat here. is that whilst the open models are tracking proprietary models quite closely, the closed models on the screen that you see come at a higher cost, as well as at like a higher token budget, meaning like you have to reason for longer and so on to get to the same stage. Whilst now we've established that open models are sort of OK, the next question comes is like, are these easy to use? Surely, like you have to deal with like model weights, you have to deal with different runners, you have to deal with setting up your virtual machine, and so on and so forth. So surely this must be like difficult to deal with. Well, let's look at it. There are typically 3 ways of like working with open LLMs. Number 1 is a serverless API. This is similar to how you would interact with OpenAI, with Anthropic, with Gemini, and so on and so forth, which is essentially that you take like a 5-line snippet, you give the model ID, and you pass a prompt in, and you get some sort of generation out. Second is a managed deployment, wherein you select the model weight, you click on a few buttons, and automatically this a provider, this could be similar to Modal Labs, could be similar to Koyeb, Hugging Face, and so on and so forth, would package these model weights up, and you get an endpoint out. Or last but not the least, since you have the model weights themselves, you can deploy it yourself. Which means that you set up your own virtual machine. This could be a VM right in your basement, or could be a GPU cluster on AWS, Google Cloud. Pick your favorite cloud provider, or at your company, and so on and so forth, and you set it up. Now let's look at these in a bit more detail, right? Let's talk about the serverless API. I'm pretty sure like everyone in this room would have dabbled around with a code snippet similar to this. This is like a boilerplate OpenAI chat completions code snippet that you would use to interact with GPT-4, GPT-4o, GPT-5, and the likes of it. In the year of 2025, we've adopted this as the standard. Be it chat completions API, be it responses API, you can access pretty much any open LLM with pretty much the same standard, which means you have a familiar SDK. So in this case, you can swap GPT-5 with, for example, GPT-OSS, or could be like one of the latest Quen models, and so on and so forth. You can choose by a bouquet of routers. So you could use Hugging Face inference providers, Open Router, and there are many other providers like this. So there is quite a lot of optionality for you. That's it. And then just like plug in your prompt and just go about and build your application. So it's pretty much the same experience as the frontier models, which are proprietary, and so on. You can go one level down the stack as well, which is what we were talking about in managed deployment. In this case, you typically go to a LLM market space. This could be, Hugging Face inference endpoints, Lambda Labs, Prime Intellect, Modal. There's a lot of competition. There's a lot of healthy competition out there, healthy providers out there, each trying to give the best sort of service to you. Pick your own GPU. This could be an H100, A100, T4, L4, whatever works with your budget size, whatever works for your specific use case. And that's it. And then just deploy. Like in most cases, it is as the image on the slide is. You pretty much just select a model. In this case, we select Quen Next, and you just hit deploy, right? And that's it. And within like 2 or 3 minutes, you have a deployed endpoint that you can then use. Last but not the least is how to use is if you want to sort of deploy these models yourself. You might want to do this in case you want to have the maximum control. You want to sort of make sure that wherever your prompts go is something that you want to have full control on. You want to make sure that the model abides by your specific rule cases and so on. In this case, you would typically start by choosing your own inference engine. there is a huge variety of inference engines, namely VLLM, SGLang, TGI. There's a lot of other like niche inference engines which you can choose from. Once you've choose these inference engines, you provision your own sort of cloud GPU cluster. This could also be just like a GPU lying in your basement, and you set it up, and that's it. And you have like a private and secure deployment. Each of the three sort of ways that I spoke about have their own utility, right? So if you want to like run fast, you would probably want to start with something which is serverless. If you want to have a bit more control and you want to make sure that the net intelligence that you supply to your app without having like a dedicated DevOps or MLOps team, then you might want to look at managed deployments. If you want to have like really a lot of control on like what is going through, you want to have full provenance of your prompts, you want to have full provenance of your outputs, then you want to sort of have something that you want to deploy yourself. The best part about this all is that given you have the model weights, you have the optionality to choose, essentially. And you can go through the stack, you can work through the competition, you can work through all the platforms and so on. But now you might be asking, like, why do I even need so many deployment options, right? This is a classic sort of buy versus build sort of argument. No matter where you are in your sort of like life cycle of a startup, of a business, and so on, you want to always increase the optionality that you have with respect to what you're providing, right? So in case like your startup or your application depends on LLMs, you want to have it. You want to always have like one failover over the other. You don't want to always depend on just one provider. Case in point is the recent issues faced by Anthropic. No shade to Anthropic. I use Claude every day. If there's someone here from Anthropic, I love you guys. But this is a recent blog post from them, which was about the timelines of issues that they faced while serving Claude Sonnet, as well as, if I'm not mistaken, Opus models. And the issues here specifically was that they had like an issue with like context window. They had an issue with the way they were routing the prompts. And what all of this led to is that you were calling the Anthropic models the same way as you were, but a small percentage of these requests were not being fulfilled the way they were supposed to, meaning you were getting like slightly lower quality outputs at the end. Given you have no sort of visibility into what's going wrong, this can cause like quite a bit of issues, because without having any visibility on what's going wrong up the stack, you just get degraded outputs. And this is something that, based on whatever use you're working on, you would want to optimize, right? And of course, like we've all heard the lore, right? Like Sonnet is dumber during the day, but it becomes much smarter during the evening. Like when you're coding in the night, like Claude Sonnet is much nicer, and so on. And of course, a lot of this is placebo. But the fact that we don't really have access to the model weights makes it much difficult to be able to narrow it down to one thing. And as one of my favorite researchers that I look up to quite a bit, Andreas says, not your weights, not your brain. And again, like you want to have as much optionality as possible, and so on. So now that we've established that open LLMs are good enough, open LLMs are there are quite a lot of options for you to use these LLMs. Let's look at some of the recent trends in the open LLM landscape. So we'll go through 3 trends. The first one is up until like last year, up until December of 2024, OpenAI O1 was the state-of-the-art reasoning model. And when they released the model, it was one of the first sort of thinking model, in the sense that before you get to the final response, the model sort of contemplates about the response itself, and because it contemplates, you get a higher quality of output. When they released the model, they they decided to hide these chain of thoughts or like this contemplation from the model itself. Fast forward to January of 2025, DeepSeek, one of the key LLM players from China, released DeepSeek R1. This was a very huge 685 billion parameter model, MIT licensed, meaning you can use it for commercial use cases. You can use it for any of your own bespoke use cases. They released this model, which was competitive with OpenAI O1, with Gemini at that time, and a lot of the models. The best part about this was that they opened the entire chain of thought for anyone to use, which means that chain of thought was not sort of commoditized anymore. Any sort of open participant, any startup, any business could have the same sort of capability of getting higher result from the same model from there on. In fact, they didn't just stop there. They proved that because the chain of the thoughts because the chain of thought is now public, you can distill this chain of thought to smaller models. The way they proved this was by distilling the R1 chain of thoughts into a smaller Qwen 8B LLM. And to their surprise, when they trained it specifically on math, this model beat a 25 times larger open model. So that's an 8B model sort of beating a 235 billion parameter model. And this is where the sort of reasoning revolution sort of started in this year. And now pretty much reasoning has become like a standard across all models. In fact, the recent GPT-5 series models, all of the models have reasoning, except they have like a reasoning effort, so the models can have, low reasoning effort, medium reasoning effort, high reasoning effort, and so on and so forth. And pretty much all open models have a thinking variant, have a non-thinking variant, and so on. Next, in general, LLMs are as good as the amount of context you give them, right? So the more context you give them, the better they would be at their downstream task. Let's say you want to summarize a research paper. If you just provide the abstract of the research paper to the LLM, the output itself would be quite suboptimal. But at the same time, if you, to the same LLM, with the same prompt, if you provide the entirety of the research paper, the summary of the research paper would be much more guided, would be much more on point, and so on and so forth. What this means is that these LLMs require a ton of context to be effective. Back in 2024, your average open LLM had a really small context. So 32K to like 64K tokens was kind of like the standard. Like, you would see your Llama, you would see your Qwen and Gemma and so on, and they would pretty much range around 32 to 64K, which means that they were good enough, but they weren't really like useful for like large context tasks, as OpenAI was, or probably Anthropic was, and so on. Fast forward to 2025, 128K, 256K has become the standard, which means that now all the other use cases that you had to previously depend on proprietary models for, you can do the same with like open models. And not just that, 1 million context even is now feasible. This is also feasible with like proprietary models, so this is not something new, but we have Qwen models which are capable of 1 million context. We have Llama 4, which is capable of even 10 million context. So you really are now not bounded by the context itself. You can really like just try a lot of these experiments. As we started sort of increasing in this context, right? Like as we started being able to sort of squeeze in as much information to these models, there was another interesting trend, which is that the cost of these models also started decreasing. A lot of this sort of came from like optimizations at the software level, at the hardware level, as well as at the architecture level. But the fact of the matter is, if you had €1 or $1, you get much more bang for buck now as you got the same time last year, right? This is again like a chart explaining the same thing from the good folks at Artificial Analysis, and so on. Heading to the third trend, back in 2024, open LLMs required a steep learning curve. There were a lot of problems. So for you to be able to deploy a local LLM, you had to look whether or not the chat template is correct. So chat template is a way in which your model learns how to map an input to an output. So if you say, hey, summarize this paper, it would take this, it would format it in a way that the LLM understands, and then you get an output. And these were quite malformed. We didn't have any sort of standards. Tool calls were very difficult. We had model precision issues. So essentially, we didn't know what was the model trained, whatever precision the model was trained on versus whatever precision the model was deployed on. So there were quite a lot of issues like this. And of course, there was latency issues and memory requirements for those. Fast forward to 2025, we now have standards for chat templates. So everyone has defaulted to chat-ML format. 4-bit and 8-bit quantization has become first-class citizen. In fact, all the new LLMs that you see are pretty much FP8 first, which means that you do not require as much VRAM on your GPU to use these, and these are native, which means that you don't really lose out on any of the performance. And in fact, now with the recent OpenAI GPT OSS, we've seen that 4-bit is also becoming kind of like a standard. But surely there has to be a catch, right? All of this is too good to be true, right? And in some cases, maybe it is. Let's look at where do proprietary models still win today. First of all, for general reasoning. So what we've seen is that open models are very good at certain specific tasks. So you would see open models being really good at, for example, tool calling, really good at math, really good at science, really good at coding, and so on. But there's no one model which is good at everything, much like what your proprietary models offer, similar to Anthropic, similar to OpenAI, and so on and so forth. So there is still a hill to climb for general purpose reasoning when it comes to it. End-to-end multimodal is quite superior for proprietary models, and more specifically for, in this case, OpenAI. OpenAI has a huge sort of margin when it comes to GPT real-time, GPT-4o, advanced voice mode. Just the fact that you can have an actual 5-minute chat with the advanced voice mode, tell it whether you want to go whether you want to ask it to go fast, slow, or ask you to teach sort of French, ask you to teach German, whatever it may be. You can just ask things when it comes to advanced voice mode and also GPT real-time. This is something which we haven't really gotten to when it comes to open ecosystem yet. Last but not the least, proprietary models have a sort of very nice, well-defined safety and jailbreak scaffolding. Open models, when it comes to open models, you often have to define this yourself. You have to make sure that they are, covered from all sorts of issues or all sorts of potential jailbreaks and so on. And this is something which proprietary models have kind of mastered at this point. So if we were to sort of summarize this in one slide, what would be a playbook for you to simply just try open models is pick your simple project, any project that there may be, swap the proprietary with the open model, evaluate on the same tests that you have been evaluating on, iterate, swap with another model, tune your prompt, and let it rip, pretty much. Last but not the least, what's next, and what is some stuff that I'm quite excited about from these trends? First of all, I'm quite excited about smaller and domain-specific models. In the recent times, the Gemma team at Google DeepMind released a Gemma 290 million parameter LLM. It's a small multilingual LLM which can run on your browser, can run on your devices, and so on. And these sort of small domain models are in my opinion, the way to go. Like you lower the cost, you increase the access to a lot more people, and so on. Second is effort-based reasoning. So this has started to become like a thing which OpenAI is doing, which is essentially from the same model, you can just define what kind of effort do you want from the model. So do you want like a low reasoning effort, a medium reasoning effort, or a high reasoning effort? And this effectively makes your singular model effectively 3 models, and for the same deployment, you get much more bang for the buck. Better quantization schemes, so FP4 becoming like a norm, and 4-bit quantization becoming like the go-to for all deployments. And last but not the least, like sparse and faster MOE. So at this point, we all know that all major frontier LLMs are MOE, which is mixture of experts. And the sparser the MOE is, the lesser the active parameters and the faster the inference would be. And we're seeing quite a lot of, we're seeing some trends towards like sparser MOEs, and I hope the community decides to sort of double down on that. That's it, I would recommend be close to the source, and always default to open. Thank you very much.
Thanks, VB. Please, let's give it up for VB.
Thank you.
And if you have any questions for him, I believe you're still around, right?
Yeah. I'm outside. Yeah.
Awesome. Cool. Yeah, thank you. All right. So our next speaker built machine learning infrastructure at Uber, Apple, and Adobe before she co-founded Arize AI. She also been recognized on Forbes 30 under 30 list for her impact on AI. Today, she'll show us why system prompts shouldn't stay static and how agents can actually evolve their instructions in the real-world environments. Please join me in welcoming to the stage Chief Product Officer at Arize AI, Aparna Dhinakaran.
Hey everyone, welcome. All right, today I'm going to talk to you all about prompt learning. Hopefully we have a good next 20 minutes together. So a little bit about what I do. One of the founders of Arize AI. Arize AI is one of the leaders in AI observability. We help teams go all the way from development to production. So we help teams actually trace their applications, evaluate them. We're going to talk a little bit about Swix's controversial statements today. About the evals really matter, and then also actually help them develop and iterate using prompt iteration. So let's jump into it. So this is actually a real post from Hacker News that I just put on the slide, which is, I think, just really emblematic of what people are feeling today. Somebody's asking, are there any real examples of AI agents doing work? And he's asking kind of, anyone have an example which I understand to be intelligent that isn't just a glorified or rebranded workflow automation? And I think you get a sense of this kind of skepticism from people who are building with agents today because they're just really brittle. It's really hard to get them to work in the real world. And I think what we're starting to see is that there's common patterns that really good agents are starting to have. And when they don't have them, they tend to be brittle. One of them is the system instructions, if they remain static and they're not consistently kind of being updated. This is what we're going to dive into today. That tends to keep it so that the agent doesn't actually learn from its environment. You have, I think there's screenshots now of all the to-do lists inside of Cursor and inside of Claude, but actually planning and being able to have, planning that updates is something that's starting to become a really common pattern in agents. How they call tools or the guidance around tools tends to be something that I think some of the better agents that we're using do really well. And then context engineering is a whole domain that, when the context isn't passed correctly, either between agents in a handoff, we start to realize that this is where agents end up tending to be brittle. But today what we're going to actually talk about is system prompts. This is a really viral tweet that Andrea Karpathy kind of tweeted in May. And I think he's actually starting to hit on something which is really interesting in this space. What he's talking about here is that there's a major paradigm kind of missing for LLM learning. He's given it a name, system prompt learning. There's like pre-trainings for knowledge, fine-tunings for habitual behavior. But there's a lot of human learning that actually feels like a change in the system prompt. So you learn something from your environment. Something doesn't go right. You end up taking a note for yourself. Hey, next time I see this scenario, I'm going to act like this. And this needs to go somewhere. And if you end up putting it in pre-training, I mean, that's a lot of work. It's a significant amount of effort. You can do it in fine-tuning. Again, significant amount of work. But you actually have English feedback and an explanation that you can just put in to the system prompt. And this is significantly kind of higher dimensional feedback than just a scalar score with typical, if many of you guys are familiar with like RL type of approaches. And so why not use these system prompts to actually pass in this type of feedback and make sure that the system prompts don't just remain static? This is actually Claude's system prompt that got leaked on GitHub a couple of months ago. 24,000 characters, 18K words. And you can see here that it's pretty detailed in terms of all sorts of conditions and how Claude should behave. And I think the key takeaway from this is that this didn't happen in a single iteration. No one just wrote the system prompt overnight and then put it into production. This was meticulously shaped over collecting data, looking at where Claude didn't do well, and then actually using that to iterate on the system prompt. If there's anything you take away from everything I've said so far, it's that the system prompts are actually really key to building effective agents. And as agent builders here, that is something that you can actively shape. And there's all sorts of different prompt optimization approaches that we're going to talk through today that you have in your toolkit. There's kind of the old approach, which is more traditional RL type approaches. So the traditional RL type approach, what you have is a scalar reward. You have a scalar reward. There's some sort of gradient descent type algorithm that actually uses it to go update the RL system. Requires a lot of examples. It's really expensive in this world. There's other type of approach called meta prompting, where basically you are now actually updating the prompt itself, but you're still using kind of a scalar score to identify what are the tweaks in the prompt, the system prompt you should actually make. What we're going to be talking about today is kind of a new approach, prompt learning, inspired by Karpathy, which actually uses the English feedback, so not just the scalar scores, but it actually uses the English feedback to improve the prompt. And I'm going to show you on actually an agent, a type of agent that's really successful coding agents. So just to recap on what system prompt learning is, it basically takes the data, so this is the inputs, the outputs, also the explanations or the annotations. It takes the original prompt, you're going to pass that into a meta prompt, and then you're going to get a new prompt. This is kind of the theory. Let's see how this actually works. We put this to test, and I'm going to run you through the benchmarks that we did on the Klein system prompt. So for those of you who don't know what Klein is one of the leading open source agents, coding agents. So the entire kind of, it's entirely open source. You can go look at the system prompt today. We heavily cut the system prompt. It's like 30 pages long. But the system prompt basically has, whatever the system prompt is, and then a section where you can actually add rules. So if you're familiar with like cursor rules, Klein also has something like, its own rules that you can go in and add. Typically, when you use the out-of-the-box Klein, the rules are empty. So we started off with kind of this was the system prompt with empty rules. And the first thing we did was run an initial benchmark. How does the initial kind of system prompt do just on its own without any modifications? We tested it on SweBench Lite. SweBench Lite is like 300 plus software engineering problems. And we ran kind of Klein on plan mode on SweBench Lite. So Klein, just for context, has both plan mode and act mode. Plan mode is basically where it generates a plan, but it's not actually generating the actual code and then running the code on the actual problem. We're actually currently working on act mode results, so hopefully I'll tweet about this soon. But we tested this using plan mode. And in plan mode, I mean, the results were, okay, as you can see, it's not great, but like around 31%, basically on SweBench Lite. And if you go in and you actually look at what, where Klein actually fails, these are some type of examples, just to kind of build some intuition. So this is actually one of the problems from a library called Marshmallow. It converts complex data types. And Klein was asked to fix some type of bug where the program, if the input was none, then the program used to just crash. So can you handle that better? So client basically, just did exactly that. If data is none, just return. But it fixed just that single case. But the input type can actually be not just a single kind of word. It can actually be a list. It can be a complex data type. So it actually has to go in and check all these different scenarios before it can just return. So this was one type of scenario where client jumped to a very minimal fix without looking at what are all the different types of cases that input can be. Here's another one that kind of initially it failed at. Another kind of repository, SymPy, Python library for kind of symbolic mathematics, where basically if there was some sort of operand like 2 times a matrix, but you had some other type of operand like an @ sign, it would incorrectly behave like multiplication instead of just failing. What it should do is just like raise some type of error or suggest some type of fix. In this scenario, what it basically did was that it actually it ignored kind of the actual Python language kind of contract around what you should do if it's the fallback option for Python, and it wrote some sort of ad hoc fix which didn't take care of multiple scenarios. Again, another type of situation where the fix kind of looked right, but you dug in deeper and it wasn't actually the right solution. So we decided to go and actually test out prompt learning on this. We took kind of original Klein on the original kind of system prompt that it came with. We ran it across the entire kind of Swibench Lite on all the sets of problems, and it generated a whole suite of actually outputs. We then took those outputs, and then the test set we tested on, Swibench, actually had a golden data set. So it had the ground truth basically with the actual kind of PR, with the actual test patch, and we passed the solution that Klein generated against the golden data set or the ground truth, and we asked an LLM as a judge to actually evaluate, is this the right solution? Did it generate a plan that would actually solve this problem? We wrote a whole template. We passed those inputs in. And this is a key part that's important here. We not only just asked like correct, false, we actually asked to give an explanation. So why was it wrong? Give me a reason why. And this is important because whether you do this using an LLM as a judge or whether you do this using a human annotation, this is the English feedback that Karpathy was actually talking about in his tweet. This is the higher dimensional feedback that an LLM can actually take and use to update its system prompt rules. So we took these explanations and we passed all of this into the meta prompt. So the meta prompt now has the original prompt that we started out with, which remember had no rules. We then passed in this data. This data is what was the problem to solve, what was the solution that client came up with, and then here's the whether it got it right or wrong, along with the explanation. All of this got passed into the meta prompt, and there's a lot here to unpack around how do you manage the context window, like will all of this fit, how many examples, hold that thought for a bit. But basically, all of this goes inside the meta prompt, and we were able to generate kind of a new system prompt. So this is just like a diff view telling you in the old world, the rules were empty. In the new world, there's all of these rules, and I couldn't fit it all on a slide, but even in something like 5-10 loops that we did, there was close to 100 different rules. All of these different types of use cases and errors that Klein would make, and all of these got passed into the rule section. So fun fact, if you're using Cursor, if you're using Klein, this is actually something you can do today. So all of these goes into the rule. You might be asking, okay, well, does this really work? Like, what was the performance? Tell me what the benchmarks were. Okay, before I get into that, I'll just tease a little bit with the same problems that we saw earlier. So this is one where it was performing on that Marshmallow library, the SymPy library. Both of these, we actually reran this with the new updated system prompt. This time it was actually able to generate a correct solution. It's actually each one of them had a corresponding rule that was in the rules that was added to the system prompt. And overall, I think with about 5 to 10 loops, we actually saw about 15% accuracy in kind of the test performance. So something around like 30% to like 45% accuracy after 10 loops. We did a typical, just in case any of you are curious, Swibench Lite. We broke it up 50% train, 50% test, and we ran this across 300 kind of software engineering problems. And this took probably about 5 to 10 loops to see some sort of improvement. We also tested this on BBH, which is known for being much more difficult tasks for language models. And BBH actually has different categories of software engineering problems. And I think what we were really excited about, and we're going to share some of these results more publicly soon, but some of the more harder types of problems like salient translation error detection or snarks, we actually saw, even after just 5 loops, something that the LLM was, client was not doing so well on, able to see pretty massive jump in terms of performance, and actually very minimal kind of regressions in some of the other categories. So this is one where just adding the annotations and adding where actually it didn't go well was something that was able to see some pretty incredible improvements. So what's the takeaways for this group, for agent builders? We just ran this on some of the hardest, you would say most successful types of agents out there, which are coding agents. I think the key takeaway that we wanted to share with you guys is, one, collecting those errors and actually either running evals or doing any kind of annotations on them is actually really important, because you won't really be able to understand what to go fix if you're not collecting those examples. This is an example of basically one of the things that we do, which is where you trace the entire application. This is typically when you hear people talk about things like online evaluation versus offline evaluation. I mean, I think one of the things that Swix was saying yesterday in his keynote was like evals, should they really be blockers before you ship something into production? I actually really don't think they should be. I think you should ship things, you should put them into production. But I think what most people actually don't talk about is that online evals, actually running evals in production on top of your data, is probably way more important, because now you actually have the data, the traces, your logs that you can then use to identify what's working, what's not working. And that's more important because it's your own data. You're not writing some BS tests that you're using as a blocker before you roll it out. You're actually evaluating your traces, and then you trust those traces to then go back and feed it into iteration. You use, just like we did where we grabbed those annotations, we fed them back into prompt iteration. But while we were iterating, we were running those same evals. This is just an experimentation view where we tested those system prompt changes, we tested what rules were better, and we actually used that as almost like unit testing before we deployed it into production. And so when people tell you, oh, run evals offline, run it before you deploy, I think the way we think about it is that those are unit tests. And unit tests are important, but you can think about them as, I always think real data, real production systems, getting visibility into that is often more important. Some of you guys might ask, okay, well, did prompt learning only work on coding agents? Do you really see it useful in other domains? Prompt learning is actually, we've been using it across a lot of different domains. We use it with a ton of our customers and use cases, even our own agent actually. This is another set of results that we've published around structured JSON web page generation, so more structured outputs. Basically, after 5 loops, we were able to see significant increases in kind of accuracy again here. This is interesting. We're basically here, the more the rule set kind of grew, you can see here that didn't necessarily always mean that accuracy was going to be consistently up. So actually having a differentiation in basically how much rules you actually pass in is something that you need to kind of iterate and tweak on in your use case. This is another use case, support query classification. So think more of like those customer support bot type agents. Here you can see here it goes vertical. So 1 loop all the way down to 5 loops. We were able to see about 8 to 9% kind of accuracy increase as we increase these. Big takeaway, I think what we're going to see a lot more this year people talk about is how are you consistently having the prompts learn from the environment. Some of these updates will be how I showed you, human in the loop, human kind of going and updating those system prompts. But I actually think a lot of those updates are going to be totally automated. You're going to collect data, you're going to run evals, you're going to run a prompt optimization approach, you're going to update your system prompt. And this is actually going to be a big paradigm shift in how people build agents. Awesome. Well, thank you so much for your time. I have any questions?
Awesome. Thank you, Aparna.
Yeah.
would like to join me for a
Yeah.
few follow-up questions, please?
Yeah, let's do it.
Awesome. Okay. Please. This was fascinating. I like that you used a software engineering engine to demonstrate that. That was pretty cool. So actually, yeah, I have a question regarding the context window since you said that
Yeah.
we're going to talk about it later.
Yeah.
Yeah, so how do you manage that?
Okay, good question. So there's kind of two maybe parts to this question that people commonly ask. One is, won't the meta prompt just become, the new prompt that's generated just becomes super big?
Yeah.
Because you have all these rules that can be generated. Is it creating like a new rule each time, every time it sees some type of error? I mean, one of the things that you can actually do is you have a meta prompt. The meta prompt, you can actually pass in rules like, hey, keep the new prompt to be of a certain length. Keep it to be X number of words. So the meta prompt actually gives you some kind of ability to force the new prompt to fit within, fit some sort of parameters so that you can't actually pass all of those kind of, rules inside of your new prompt. The next question you might be asking is, okay, well, what if I just have a lot of examples? Are all of those going to actually fit inside the meta prompt? And what does the context window management of the meta prompt actually look like? I think this one's actually the lot harder question because the more you actually have this application or this agent running in production, you're going to collect more and more scenarios of failures. That's a good thing. But every time you do these types of identifications, we see teams trying to, okay, well, this is one specific scenario, this is another specific scenario. What we end up recommending is trying to find categories of problems. So doing kind of error analysis, but also error categorization, so that you don't have to pass every type of example into the meta prompt, but you actually pass kind of examples that are replicative of a larger type of category of problems.
Okay. But when you pass on, all that data, all that information to the meta prompt, can we get to a place where we'll start seeing some degradation in the maybe in the generations?
For sure. I mean, I think this is like a classic, ML type issue where, do you get to a part where you overtrain or you overfit?
Yeah.
So you overfit the new prompt to be replicative of just your errors, but it's not actually kind of, it doesn't translate. So I think this is where it's important to have, make sure you're testing the train accuracy, seeing that the train accuracy doesn't go down, comparing that with your test, your test set, but then also having a complete blind set that you're not kind of overfitting your meta prompt to.
And also LLMs are getting so good, right? Now we have context windows of 1 million, 2 million, and I think it's only going to get better moving forward with all that infrastructure that we're building. Hopefully, this is going to happen. All right, so can you tell me more about the difference between prompt learning and how do we compare it to frameworks like DSPI?
Yeah, this is a good question. So we love DSPI. I think DSPI is awesome and kind of, I think they put out a lot of different prompt optimization approaches. I don't think about this as like a us versus them. I think there's going to be more prompt optimization techniques out there. So DSPI actually has a couple, which is slightly different strategy, maybe. So MIPRO and like the few shot learning. So some of those are a lot more, call it programmatic in that it takes a few it takes a few examples and just passes those in, and those end up becoming the actual, that ends up being passed into your new prompt. Some of them still use scalar rewards. So like I was explaining earlier, they don't actually use the English feedback, but they just use the scalar reward to actually improve the prompt. So some of those strategies are just different than what we're proposing. But actually, they did release a new approach called GEPA. This is very recent. It's philosophically similar to what we just talked about with prompt learning. So we're actually yet to run I think we're currently running some benchmarks right now on GEPA to see how it performs. So we'll probably tweet out some of those results soon.
Awesome. One final question for you. So how does the prompt improvements fit into the context window of the meta prompt?
Okay, yeah. So this is kind of what we were talking about earlier, which is like around managing your context window. I think there's probably two things that really matter in I think we think about all the time is identifying and doing error analysis is really important. So looking at your traces or your application, finding those errors, and then you don't have to pass every single error back into the meta prompt, but you can start to pick category, kind of examples that are reflective of an entire category. So that way you're kind of being smart about what you pass to the meta prompt.
All right. Well, thank you so much, Aparna.
Yeah.
Thanks for your time and for the talk.
Thanks, everyone.
All right.
Oh,
Let's
and
give it up.
if you're
Go ahead.
interested at all in any of the things we talked about today, there's a workshop I think my colleague's running actually on offline evaluation and prompt iteration. So it's a little bit more hands-on if you want to try it on your own agent.
Awesome. Thank you. Let's give it up for Aparna. Awesome. So our next speaker was part of the founding team of Zenly, later acquired by Snap. And he's the founder of ZML, a high-performance AI inference technology aiming to push the limits of what's possible beyond GPUs. So this is going to be fascinating. OK, today he's introducing a breakthrough attention mechanism. Please join me in welcoming to the stage founder of ZML, Steve Morin.
Hey, thank you everyone. I'm Steve, and today I'm here to talk to you about some breakthrough technology we've been, working for LLMs, which, hopefully in our hopes, pave the way for unlimited context. First of all, we are ZML or ZML, depending on which side of the Atlantic you're watching. We are building this universal inference stack and engine. So essentially, it's like literally the same code, the same binaries even, that runs on for any models on any language. Any chip. Any language model or any model on any chip. But this is not what I'm here to talk to you about today. Today we're going to do a little bit, of a deep dive into Llama and also probably one of what we think is one of the most fundamental problems in LLMs today. So this is the Llama architecture. So usually every time you generate a token, this happens. That loop you see in the middle is for each layer that happens. What we're interested today is one mechanism that is fundamental to the way Transformer works, and it's called attention. This thing happened at every single layer. There's a few operations on each layer, but this one happens every layer, and it has a tiny problem. This is the mathematical formula of attention. You don't need to get into the details, but the problem we all have with attention, and ultimately that binds everything we see from the hardware to the reason there's a context window, etc., is because that algorithm runs in quadratic complexity. Which means for everything you add to the algorithm, you get to do the square of it. And that makes us pretty sad and also pretty limited in what we can do. But there's something about that formula. Like if you squint your eyes real quick, you might see something that is of interest. And that interest is the softmax, right? So what's with the softmax? Well, this is the equation of the softmax. And long story short, you don't need to read it, but it's essentially exponential of all the elements divided by the sum of the exponential. And what that means, it means that tiny signals becomes a lot bigger. And what is the end result in the end? The end result is that this is an actual, output of an attention for tokens. And what you can see is that it's mostly sparse. There's a lot of empty room. So there's, in the end, a lot of completely close to useless calculations that are being done every time you run that algorithm. So, as an ex-engineer, an ex-backend engineer myself, I look at this and I squint my eyes and I see, well, is this a graph really? Could we only do the yellow dots, right, and not do the black dots, right? The GPU will compute everything. So, is this a graph, right? And turns out, yes, it is. Very much a graph. It's a graph in latent space, but still a graph. And what's very cool about the fact that, if we model this thing to be a graph problem instead of a pure raw matrix multiplication, is that we can run it in log of n. And as you can see on that graph, log of n is, flattens as the context sizes augments, right? And this, paves the way for unlimited context ultimately, because it's log of n and it's not, n square anymore. But it's very nice, very promising, but there's this tiny, tiny problem. The tiny problem is that because it's a graph, we need branching. And this means that for this, GPUs are close to useless. They're very bad at branching. They can do it, but if you have worked on GPUs, you might understand a bit deeper why. But CPUs are good, right? And we get into this thing in which we might do the calculation and we might model this as a graph problem, but only on CPU. So the question is, can we do it fast enough? Now, maybe. Let's do some math real quick. So this is the per layer. This is a layer of Llama. And what we see is like there's 32 of them in an 8B. If we want to run it at 100 tokens per second, that is 300 microseconds per layer. Now, this is like our time budget if we want to achieve that throughput, which is roughly 5090 territory. If we look at everything around attention, we see that already 200 milliseconds is off the equation because of all the other operations. That leaves us about 100 microseconds to do the actual calculation and the actual attentions. That's not a lot of time, right? So the question becomes, is it enough? Like, do we have enough time to do the calculation of attention? Number one, like the vector and the matrix multiplication, etc., as a graph on the CPU, and all of this in less than 100 microseconds. And actually, we can. And the reason we can is that because we only compute essentially the yellow dots, right? So this is what you see as a trace of a whole one layer. And so that is pretty interesting, or at least encouraging, because we only spent about 30 microseconds doing the actual calculation. And remember, we skip the black parts. But there's another side benefit to that, because if we run the attention on the CPU and not on the GPU, it means that we have more GPU memory. In this case, if you run a model on the GPU, you have part of the GPU dedicated to the model, and part of the GPU, sometimes the majority of the GPU, dedicated to the KV cache. That creates a plethora of problems for those who are deploying LLMs in production environments, static routing, and all of these things. But if we do the attention on the CPU in system memory, then suddenly the KV cache doesn't need to live in the GPU, which gives us more memory for the model, and actually makes also the model completely stateless. The GPU, sorry, completely stateless. And so in this case, KV cache now lives in system memory. The GPU will send data to the CPU. The CPU will run the calculations, update the KV cache, and send back the attention to the GPU. But there's another catch to this, is that we are in need of a lot of CPU cores then, roughly about 1 per KV head. So the question is, like, how do we get these cores? Like, let's say we want to do a batch run. So perhaps, is there a way we could get these cores, maybe not locally on the machine, which has sometimes, underpowered CPU because they're pretty much useless, except for PCI lanes, maybe. But could we get them, like, these cores somewhere else? Because remember, now the attention and the KV cache is completely separate from the GPU. And so maybe, could we get, this CPU power over the network? Remember, we spent about 30 microseconds or so on the raw calculation. That leaves us about 70 microseconds to, let's say, to attain this throughput. So let's do, is physics on our side? Not easy. Let's do some calculations. So roughly, the payload we would need to send is the number of attention heads, KV heads, etc., which is about 10K for an 8B per layer per request. Now, let's be conservative about this, and maybe we're running on a 10 gigabit internet connection, right? So no InfiniBand, no crazy stuff, somewhat, I would say, premium 10 gigabit, but it's not the end of the world, and it's not very, I would say, unattainable. And physics tell us that we could run this thing, at least do the round trip of the data, would go at about 16 microseconds. So suddenly, we might ask ourselves, are we ready to spend 15% of the time budget on essentially unlimited CPU cores because we can provision and unprovision them over the network? I think that's a pretty good deal, if you ask me. And so this is what it would look like. So you would do the calculations, the dense calculations on the GPU, then extract the data, send it over the network as UDP, of course, because you want to be compatible, feed it to the other machine, compute the attention on the CPU, and send everything back. And you need to do this faster than the GPU would calculate it himself. Now, the reason we cheat is that we do much less calculations than the GPU would. So, I mean, let's try it, right? Let's do a ping. And, oh man, oh crap. So, physics is on our side, but engineering obviously isn't. So how do we square that circle, right? Something's got to give. There must be something we can do because, you know, physics is on our side. We're not, at least at this point, we're not fighting physics. So maybe we have a little trick up our sleeve we can pull. And it's time for kernel bypass. And so the Linux kernel, we are at this stage, you know, thankfully for us, or maybe not so thankfully for us, at which the Linux kernel might be too slow for what we are trying to do. There's too much latency. And so this is where we enter another technology in the mix, and it's called DPDK for those who recognize it. What it allows for us is directly talk to the network card in a way that is very, very low latency. The driver is actually built inside the application itself. And what this allows us is to get much, much closer to the theoretical latency. So theoretical latency in this case would be about 16 microseconds. We get about 20 measured. So that is, you know, still within the budget. And this is exactly what we've been building. And we call it attention D. And the clicker has a slight lag. And if you're up for it, I'm here to give you a demo. Are we good? All right. So just so you know, this is what it's running on. Right? So what you see is like a machine with GPUs and a machine without. All the attention is running on the machine without the GPU. So nothing is missing, right? So let's crack this one. Can you see it? Nope, but it's fine because I can do this and that. Right, okay. All right, so of course this is a video because demo gods, right? But what you see on the left is attention D running. On the left machine, you see all the cores 100%. And what you'll see on the right is a standard Llama model running standard inference. There's nothing happening on the model side. They're communicating over the network, and you know, I'll let you see what it, you know, how it performs. So we're loading the weights, and then off it goes. But oh, where's my? I have lost the quick time. Okay. But we're not done. I think you are in luck because maybe we can do a little bit more than this. You see, the KV cache is not on the GPU anymore. That leaves us more room. So maybe what if we could fill the entire GPU without any, you know, room for conversation, any room for the KV cache, only the model, completely stateless on the GPU. And so this is what we have for you, a live demo I'm actually going to do, as we speak, in which we're going to run a 32B model, FP8, on a 32 gigabyte GPU, which is, as far as we know, has never been done, because it's useless in the real world, except if you have this. All right, so, I have the feedback here, good. So are we live? Okay. Hopefully the Wi-Fi is with us. So I'm going to run attention D on the bottom terminal. Yeah, it's live. And on the top terminal, I'm going to run a 32B model, Qwen 3 32B, on a 32 GPU. Just so you know, 32 gigabyte GPU. Just so you know, that model fits, when it's done loading, there's 20 megabytes remaining in the GPU. So essentially useless. So let's try it. I'm going to tell it to write an MLP CUDA kernel. Hopefully it doesn't crash. It crashed. That's how you know it's a real demo, right? And there we go. So just so you know, this is, as far as we know, it's the first time it's ever been done. That model isn't supposed to run. Thank you. So, and just so you know that it's not, a fake thing, I'm going to kill attention D, and yes, generation stops, because it's now, shooting packets into the void. All right, let me just go back. So the demo gods were with us today. Pretty good. Thank you very much. That is us. Feel free to, or be sure to check out our repo. This is open source technology. And would love to see you part of the community. Thank you.
Amazing talk and demo. Would like to join me for a few questions?
Yeah, sure.
All right. Okay. You can have a water.
Thank you.
Yeah.
It's surprisingly hot.
I know, right? Especially when you're on a live demo.
Right.
And you don't know if it's going to crash, not crash. Yes. All right, so I'm going to start with the elephant in the room. What is written on your T-shirt?
So for those like me and like our team, which are terminally online, this is a reference for Zuck.
Okay.
It was he had like this shirt, but it means essentially ZML or nothing. And he had like a Zuck or nothing. So I'm like, well, no, this is us, right?
It's ZML now,
right,
it's not Zuck. All right. Okay, so you touched on branching, and you said the GPUs are bad at branching. Can you explain that to the rest of us who don't understand?
Yeah. Well, GPU are very good at parallel processing, and the reason is they operate in a mode called SIMT, single instruction, multiple threads. And so when you have branching, so we can go into the nitty-gritty details, but at least
let's do it.
Bird eye. We can, because there's like warps and SM, etc. But long story short, when there's a branch in GPU code, the cores that are going to do one side of the branch will wait for the other side to finish.
Yeah.
So essentially, if let's say you have modulus 2, and you want to have the GPU to work, let's say, on odd numbers and the other one on even, and you do an if in the middle, half of the GPU will always be asleep waiting for the other side, because the instruction sequence is common to at least the whole, I would say, group of processing. So they're really bad at doing this, which is why people spend a lot of time trying to do clever tricks, etc. But it's very good if you're like doing image processing, for instance, because it's always the same thing you do for every pixel. Or matrix multiplications, for that matter.
All right. Okay. You showed this and you spoke about attention. So I'm wondering if this is specific to related to the transformers architecture, or can we imagine other architectures also being compatible with?
At least it's related. So the transformer architecture uses attention. There's other architecture that are using, like everybody is rushing against that n square. N square is the reason we have HBM. It's the reason data sizes are shrinking, are trying to shrink, quantization, and so on. So it's part of the transformer architecture, at least attention, but not only. Sometimes you see, like, I would say, assemblies of common architectures, and there are also some linear architectures, Memba, for instance. But for now, at least, for a good while, everybody's trying to unseat it. It hasn't been unseated.
Yeah, transformers are here.
Yeah, for now at least,
for
until next time. Famous last word, right? But
yeah, I had one more question for you, if that's all right. Okay. So I think where do you see ZML going after this? Like, what would you like the community to do with it? Obviously, it's open source. I see that we have a GitHub link here. What do you think is the next step for it?
As a community, I mean, what we're about is being very, very radical about inference at essentially all the layer in the stack, from single-digit microsecond stuff to high throughput, whatever. Loading a model in we have benches in which we load like an entire model in like 1 second from SSD. So we're very, very radical about very high performance, very low level, and building the tools to achieve this, right? Number one, it's way too expensive, but also we haven't been compute bound in a long time. And so what we're trying to push with ZML is how can we build an ecosystem, a software stack, a product line, which is entirely built around the thesis, which is universal, chip support, very low latency, everything is a hot pass, type of thing. Because that, attention mechanism, we demoed, you could, in theory, implement it in PyTorch, right? But it would run at like maybe a token per second, because that 30 microsecond would become millisecond, right? So at some point, fighting latency is very hard, and this is what we're about, but from the ground up. And as a community, yes, we have a framework that is open source. We want people to use it. There's rough edges. We are the first users of our framework, so bear with us. And it's constantly changing, etc. But it's improving very, very fast. And we have some cool demos. Many, many more incoming.
Awesome. So pushing the boundaries of physics and trying to make physics on your side and
stay compatible, but stay closer, I would say, to physics.
Awesome. Well, thank you so much, Steve.
Thank you.
That was fascinating.
Thanks, man.
All right.
Thank
you. Let's give it up for Steve one more time, please. All right. Okay, so we're back at 4:30. Now it's time for a well-deserved break. So we still have coffee by our friends from Tinfoil. So I'll see you here at 4:30. Thank you.
Ladies and gentlemen, please join me in welcoming to the stage your MC for the AI Engineer Paris, Developer Experience Engineer, Ralph Chabry.
Yes. All right. Welcome back to the main stage. We still have 3 amazing speakers left, so I hope you're gonna enjoy this. I know that we had a lot of speakers have prepared a lot for this. So up next is our developer relations engineer at Llama Index, where she helps developers build product-ready agentic applications. Today, she's here to show us realistic abstractions on how to build an alternative to Notebook LM. So you got to pay attention to this. Please join me in welcoming to the stage Developer Relations Engineer at Llama Index, Tuana Celik.
Hello, everyone. It's great to be here at the first AI engineer in Europe. Let me just make sure the screen is on. All right. So hopefully I can get my slides up. And I'm going to be talking about building a Notebook LM alternative, fully open source. And hopefully I can inspire some of you to try it out. Without further ado, this is me. My name is Tuana, although you just had an introduction. And I have been with Llama Index since May. So why Notebook LM? Well, Notebook LM is pretty cool. If you have not used Notebook LM yet, I am going to show you quickly what it's all about. And this whole talk is about realistically what are the abstractions we need to actually build an alternative to Notebook LM. So this is Notebook LM. When you start up a notebook in Notebook LM, you're greeted by this kind of page where you're asked to drag and drop maybe a file, or you can also link it up to your Google Workspace, provided some URLs, YouTube links, or simply copy-paste content in there. And what you get out of it is actually a lot of stuff. So here you see me the other day. I've provided a document on an IKEA guide to build a kitchen. And you have a summary here. You can do some question answering, and you can do so much more. On the right-hand side, you see that you can get an audio overview. You can get sort of flashcards for an FAQ. You can get even a video generated. And one of our favorites, you can also create a mind map out of the whole context present in your document, which is a great way to abstract over all of the information present in your document and kind of make it easier to think about. So we set ourselves a challenge. And we also decided to make our lives a bit difficult by setting ourselves these challenges, because we really wanted to focus on creating an alternative, but we wanted to make sure we were doing it justice. So these are the 3 main things we wanted to focus on. We wanted to be able to provide complex documents. And when I say complex documents, I'm talking about documents that maybe that have tables, images, what I love to call a layout bonanza, because not every document is uniform in the layout. We also wanted to make it, and this is, I'm going to show you later what was really the pain. We wanted to make it reusable, especially the functionality and tools that we were building. Again, this is an open source project. We wanted it so that you can go ahead and use any of those tools and functionality separately without it having to be our project that you're using it with. And finally, and you'll see why this is important, we also wanted to have some level of control over the flow, which is where things start to differ to what you might perceive as classic agents, where agents get all the agency to decide what to run when. We wanted to make it so that we had a bit more control over the process. And it so happens that I work at a company that provides many tools and products that help us get to this project and make it easy to build. So I'm going to talk about Llama Index very briefly. We have two main sets of products at Llama Index. A lot of you, I hope some of you, know about Llama Index, the open source framework that allows you to build your own agents and design your own logic. That is our open source framework. That is one layer. But we also have Llama Cloud. And Llama Cloud has quite a few products now. It's growing every day, which provides tools and products that allow you to parse complex documents, extract structured information out of them. You can also use Llama Cloud as your own vector store that you manage, that you use to chunk and embed your own documents as well. So great, we have some ingredients to start the process. So we set off, and the two main Llama Cloud products that we initially started with are Llama Parse and Llama Extract. So one thing we wanted to do is make sure that users that want to use what we now are going to from now on call Notebook Llama could be able to upload documents of any shape or form. So Llama Parse is super useful here. We don't worry if there's any tables, images, layout differences at all. And also Llama Extract. Llama Extract is my favorite out of the bunch. I love working with it, and a lot of the times we see people use Llama Extract in situations that are probably a lot more boring than what we're going to be talking about today, but we often see Llama Extract being used in situations like this, where you may have long, complex financial documents, and really the thing that you want to focus on is a set of information that you want to extract from it, and you really don't care about the rest. So we have here the SEC filing by NVIDIA, and we want to get from that complex PDF and just focus on a few key components from it. And you can do that in a few ways. You can either go ahead and select one of the predefined schemas we have in Llama Cloud, or if you're like me and you prefer being in code, you can go ahead and do the following, where you have a Pydantic schema. And what's important here, not only are you defining the schema, so also the data types that you're after, but you're also providing a model, again, of your choosing, a description as to what it should be looking for within the document. And this description is used to then go and extract that relevant information. And then you can go ahead and create what we call an extraction agent. You can either, again, do this within Llama Cloud or in code. You deploy an extraction agent, which can then be reused over and over again. And so here you see my extract agent for SEC filings. Now, what we noticed is that we can actually start using our very own Llama extract to start off with the creation of the initial Notebook Llama, where, again, like you saw in the original Notebook LM, you had FAQs ready, you had a mind map ready, a summary ready, etc. We decided to go ahead and use Llama Extract as a way to start the notebook up. And you'll notice here we've defined a schema where we're asking for a summary of the document, highlights, so bullet point highlights of the context in the document. We're asking for questions and answers. So that's step one. And the next thing we decided to do was make use of our framework, our open source framework, specifically the workflows, because this is a way that we can define our sort of business scope, what the agent is able to do and not able to do, and we're able to kind of architect the pathway that our application is taking without it relying on an LLM to make a decision in the first place. So we're going to see how our workflow is built a bit later on, but this is the point I want to shout out Clelia, because this is really her brainchild. This is my colleague Clelia. You can follow her on LinkedIn if you like. She's our open source engineer, and she put a lot of effort into Notebook Llama. So I hope you like it, and I hope you decide to contribute to it in the end as well. So what does Notebook Llama do? Notebook Llama, I want to point out again that this presentation, I'm definitely not presenting to you a finalized, polished product that just exists and that you can go ahead and use. Of course, you can go ahead and use it, but really our aim is that this is a start, and if you do want to contribute or you see that something's missing, it's not the complete Notebook LM replica, obviously, so please do feel free to contribute to it. And we do a few things. We do have our mind map generation. That's the first thing we decided to implement. We can ask questions and do QA over files. We're going to have a look at it in a bit. We can extract tables and images as well. We have podcast generation. We've very recently added observability to the product as well. And now I'm going to quickly show you what we can do with it. All right, so I've decided I'm not running this entirely live because I don't trust the Wi-Fi. So this is something I've done just before. And I'm going to just increase this. So here you see me uploading the IKEA kitchen guide. Once you've uploaded it, very similar to Notebook LM, we're getting a summary, we're getting bullet points, we're getting an FAQ, and we're getting a mind map that I have to be careful when I scroll over because it moves around a lot. Our mind map does not look as sleek, as you may see. It does not look as sleek as Notebook LM, but nevertheless, we have it. You also have document management, where you can look at previously uploaded documents. This is the same one, so it's not very interesting. I've tried the IKEA kitchen guide many times. And we also have document chat. So here, again, is me asking the question, what are the main steps I should take to install countertops in my new kitchen? And what I get is a very sort of in-depth answer with citations, and I can also look into a bit more detail about what the sources are and why it's claiming that this is the best way to install countertops. Now, before I switch back to the presentation, one quick thing I want to point out is let's not worry about the PDF loading, but here we see our extraction results of the IKEA kitchen guide. You saw earlier the schema that I had defined. The schema is right here, and here is the result. And you'll notice that these are the exact results you saw in the UI for Notebook Llama as well. This is how we set up the notebook. We get the extracted summary, highlighted bullet points, question and answers, and that's basically our entry point into Notebook Llama. With that, let's switch back and go on. All right, so I'm going to focus on explaining to you two main components of Notebook Llama. So let's first start off with the first homepage where we load the file and we generate the initial notebook with the mind map and the bullet points, etc. So how does that all look? We want to result in the image you see on the right-hand side. So we want to start with a PDF. Next, we want to be able to generate some sort of mind map. And next, we want to generate the whole notebook with the summary and bullet points, etc. So actually, by thinking about this, we've already kind of described to ourselves exactly what the logical flow should be, ideally. And how do we do that? In Llama Index, we have an abstraction called workflows, which is a class that you can extend to create any workflow. And a workflow really consists of two main things. You'll notice here that there are methods called steps, and steps are expecting events, and they can also emit events. In this case, you see a one-path system where we have 3 steps, each of them are expecting a certain event. But the cool thing is we can define our own events completely from scratch. So what we did is define 3 events. We've defined our own custom start event. We call that file input event, which is simply a file name. We want to end up with a stop event, which is, again, our custom stop event, and we've called that notebook output event. You'll notice that the notebook output event has the mind map, summary, highlights, etc. as well. And intermediate, we have a mind map generation event. This is, again, custom code by my colleague Clelia, where she used the summary and highlights to generate a mind map from scratch. Now we have the steps, we have to actually put it in some logical order. So again, we define our own custom steps. And the first step in the process is a step that we call extract file data. This is expecting the file input event, and it can actually branch out. We account for failures, so maybe a mind map wasn't generated for some reason, in which case we return the notebook output event, which is an empty notebook with maybe a message indicating as to why a failure happened. But if not, and if we're successful, we actually return the mind map event. mind map creation event. Next, we actually have an event called generate mind map. And this is where, in a successful scenario, we are able to generate the mind map, and now we can create what we call the notebook output event. Now, one thing you may have noticed here is actually most of the logic is within MCP tool calls. And the reason for that is the challenge we set ourselves in the first place. And we wanted to make sure that any sort of custom logic we were building into this application, we could actually put it into an MCP server and provide them as MCP tools. So if you like the functionality that you see and you want to extend the repository in any sort of way, you can use all of those tools in isolation or go ahead and actually use the mind map generator with maybe Claude. So that's the reason why we decided to put all of the main functionality in MCP tools. So let's have a look at our first tool, which we call the process file tool. And the most important thing here is the description. If you've been using MCP tools and servers with your MCP clients, you'll know that the description is pretty important because it's the one thing that the LLM has to use to decide whether it's time to run that tool or not. So we've described it as this tool is useful to process files and produce summaries, question answers, and highlights. So what's going on here is, again, you might notice there's an extract agent. This is the point in time in our workflow where we call our extraction agent to return all of the highlights and FAQs. We already have our extraction agent deployed in Llama Cloud. We don't have to worry about that. But when we hit this point in our workflow, we call that extraction agent and we wait for a structured output. Once we have that, we're done and we can actually start generating the initial notebook. Next thing is the document QA functionality you saw. And this we manage with Llama Cloud indexes as our sort of database, our vector store, if you will. And we also make use of claim verification. And for that, we have Llama Cloud indexes, which you can connect up to any of your own vector stores. And once you have your data there, you get to decide when you're at the RAG process where you want to do retrieval augmented generation or claim verification, etc. This is where we again picked to use our Llama Index open source framework, because this allowed us to make it so that you can switch around models easily, maybe build it into a completely different workflow if you wish to do so as well. So how does that look? Again, we've wrapped this in an MCP tool. We've described this as very simply query a Llama Cloud index. But you'll notice here we're pulling in a query engine called Citation Query Engine from the Llama Index framework. The LLM is, again, switchable, and the retriever is our Llama Cloud index. And simply, this tool is run whenever there's a question from a user, and we return the answer to the user in the UI as well. All right. Finally, I want to talk about something we've been working on very recently, is that now we've made it so that you can, if you have already an MCP server running with tools running, and you want to use pre-configured workflow agents with Llama Index, you can bring them in as any other tool. You might provide a Python agent or a function agent as well. So you don't have to define any tools and functions yourself. From now on, we've made it so that if there is an MCP tool out there that you want to use, you're free to do so with a Llama Index workflow or a predefined agent. The same thing is valid for all of the Llama Cloud tools that we mentioned throughout this presentation, including Llama Extract, any extract agent that you create with Llama Cloud, you can run as its own individual MCP tool. The same goes for indexes. Any indexes you may have within Llama Cloud, you can run as an MCP tool, and you describe it with your own custom definition. And that is a video of me explaining the whole process. And this is, again, an open source tool, an open source server that you can run yourself. And with that, the whole point of this presentation was hopefully that you'll try out Notebook Llama. I hope that you contribute to it, and also it's a great way to discover basically all of the products we have with Llama Index and Llama Cloud. So with that, thank you very much. And I can take questions.
Thank you, Tuana. Would you like to join me for a couple of questions,
Yeah.
please? Thank you so much for the presentation, by the way. Wow. Very nice slides, very colorful. I love it.
Thank you.
Um,
Our logo changed a bit too, so it's a bit more colorful now.
I see that. All right. Question, what's the best framework to build agents?
Ooh, spicy question. I think I love to give this answer. Everyone calls it a very political answer, but I think it's really true. They all are trying to get to the same, that it's the same means to an end. I don't know if I'm saying this correctly in English. But I think it really depends on the type of developer experience you're after. Some frameworks are a lot faster at integrating the latest research. Some frameworks are a lot more stable. Some frameworks do a great job of having observability and tracing inherently, and some focus on other more sort of AI-specific functionality. So that's my political answer to that.
Awesome.
Hope you enjoyed.
So it's Llama Index, guys. If you care about developer experience, from what I'm hearing.
Being truthful here. I'm DevRel, so there you go. That's the answer. But Llama Index.
Awesome. So yeah, you mentioned you're in DevRel, so you meet a lot of Llama Index users as well. What are some of the cool things that you see them build?
Oh, wow. That is a good question. So we have two very distinct groups of people with Llama Index users, I will say. Llama Index users seem to be a lot more creative. It is an open source product, so I guess that's expected. And Llama Cloud users are usually they're doing this for business purposes. There may be enterprise customers, etc. as well. Very fun projects. Okay, that's going to be a tough one. We had one specific use case where it's a very difficult situation, but this user was trying to use Llama Cloud to parse incredibly complex sort of architectural charts. I think it was like a system grid or something. So I think that always sticks out to me. This is a very difficult one to solve as well.
Wow, awesome. One final question.
Yes.
In the architecture overview, we also see Postgres, the base database, by the way. Just saying, no bias here. What is that used for?
So all of the data that you saw, the context and the documents you saw, are all stored in Llama Cloud. However, we do run Postgres locally, and that stores everything that the notebook Llama UI needs. So, for example, the mind map is generated, and you have an HTML content for it. We store that in Postgres so that you can go back to it.
Awesome. Thank you so much for
Thank you.
Tuana. So let's give it up for Tuana, please.
Thank you.
Thank you. All right. Are we ready for our next speaker? Yeah? Okay, let's do it. So our next speaker leads the AI developer experience at Google DeepMind, where she's helping shape how builders everywhere use the largest... It's 5 p.m. But we're going to get through this together. How builders everywhere use the latest generations of models. And I think she's going to talk about a lot of cool models today. So I'm very excited about this talk. Today, she'll take us beyond chatbots, showing us live demos on VO3, Genie 3, and Gemini 2.5 Pro. So please join me in welcoming to the stage AI developer experience at Google DeepMind, Paige Bailey.
Thank you so much. I'm so excited to be here. And even though it's 5 p.m., I think there will be some things to wake us all up later today. So hi, everyone. My name is Paige. I'm fortunate enough to be here with my excellent colleagues from Google DeepMind. Everybody from GDM, kind of raise your hand. Excellent. Amit, Guillaume, Patrick, Ian, they've all been valiantly kind of sharing demos, staffing the booth, presenting all throughout the day. And we're here today to kind of wrap it all up. Some of these things might look a little bit familiar if you were at some of our earlier talks, but hopefully there will be enough new stuff that it will be exciting even for people who might have experimented with our models before. So As mentioned, these are the folks from DeepMind who are here today. And I also just want to say that Google has been a little bit busy. If folks might have remember back to a year ago, I think there were, not as rapid of release cadences. There were fewer models released out to the market, fewer features. Over the last really year and a half, we've been kind of accelerating a pace that's really exciting to see. I'm a long-term Googler, and I've never really seen us ship at this kind of a rate. I think we're releasing a new model or a new feature every 5 days or thereabouts. A couple of these models that have been recent to market are Gemini 2.5 Pro, so show of hands, how many people have used that? Excellent. Gemini 2.5 Flash Image Preview, aka Nano Banana. How many folks have been excellent also? We're not the best at naming things. VO3, which is our video generation model, show of hands. Awesome. Gemma 3N, part of our open model family, like open source, kind of rules and fuels the world. And then Genie 3, which is also our open worlds model. So you'll see all of these today, and then also talk through some applications and when you might want to use one versus the other. So Gemini is special in a number of ways, one of which is that it's natively multimodal. It can understand video and images and audio and text and code and all of the above all at once in multiple languages, but it can also output multiple modalities. So Gemini models are kind of unique in the market in the sense that they can do many, many things. They can output text and code, but also images. They can edit images. They can output audio, like you might have seen in Guillaume's section of the workshop earlier this morning or earlier this day. But that means that you can do all sorts of things. You can have image understanding, editing, speech to text, text to speech, all kind of natively incorporated into one model, in addition to things like PDF understanding. One of the folks here today has been using Gemini to kind of pull in PDFs and extract out images, extract out bounding boxes for different geospatial coordinates, and then also using it for real-time conversations. So this is just an example of something that you can do with the Nano Banana model, give it an image of a car and have it kind of picture perfect turned into a convertible. Our robotics team has been using something called Gemini Live to kind of orchestrate many of the different robotics behaviors. Gemini being able to automatically detect bounding boxes and different features kind of helps the robotics models understand where to grip a specific object, where to head if you ask it in natural language to kind of rotate a tool or to build you a salad or something similar. We've been incorporating Gemini into our smart glasses, so it can kind of give you recommendations on the fly as you're navigating across cities. It can give you help with your math homework or your physics homework as you're looking at something on the screen. We saw this in action at Google I/O earlier this year, if you want to take a look. And it can also do things that feel a little bit like Hitchhiker's Guide to the Galaxy. So if you remember the Babelfish, where you have one person speaking in one language, and you hear it in your native language, and you speak something back and they hear it in theirs, that is possible today with the Gemini Live API, which is pretty remarkable. But I am not a fan of slides. I'm actually very bad at slides. And so I think it's much more interesting to kind of see some of these things in action in AI Studio and in some of our model scenarios. So if you haven't seen AI Studio before, this is the best place to go to get access to DeepMind's models as soon as they're released. You can select different models here off to the right, see different details about them, including details like pricing, the specific model name. So this is what you would incorporate into the API if you wanted to call that specific model. As you interact with the models, you can also click this Get Code button, and you can see the libraries called here to engage with the Gemini models. So we have a GenAI SDK, which is unified with our Vertex AI compadres over in Google Cloud. So instead of having a distinct model for the Gemini APIs and one for our enterprise customers, these are now merged for Python and for TypeScript. So if you need to toggle from one to the other, it's pretty seamless. And then we also have a couple of features like the streaming feature, generating media, build, and the like. And so hopefully folks saw our build feature a little bit earlier today. Show of hands, how many folks saw that at the expo as well as the others. Given that there are a few folks who haven't seen it, I'm going to do a live demo of build featuring the Nano Banana model, including deployment. And then we're going to race over back to show a couple of the other capabilities. So with with build, one of the fun things is that you can describe in natural language an app that you would like to create, and then you can build it in real time in the UI and deploy it via Google Cloud and Google Cloud Run. So as an example, let me toggle back. So hopefully, where did the other sort of screen go? There we go. Excellent. So with the build feature, you can describe in natural language the app that you would like to create, and you can deploy it in real time via Google Cloud. So I could say something like, create an app that takes a webcam photo of the user. The app should then use that photo to ground the creation of a, let's say, a Dungeons and Dragons character. The app should use Gemini 2.5 Flash image preview, aka Nano Banana, to modify the image to show for the D&D character, so it looks similar to the user. Make sure the app is well designed and that the stats for the character are included. And I'm going to hit Control Enter, and immediately we see Gemini 2.5 Pro kind of breaking down every step of creating this app, kind of walking through all of the different architectural considerations that it would need to make, selecting the different models that are available. And since this is baked in natively to AI Studio, it's incorporating the latest models and the latest features from the generative AI SDK. So if you ever played SimCity 2000 or any of the other kind of sim games, that loading screen probably looked a little bit similar. All of the code is getting written here onto the right. You can see this really nice file explorer here in the center. And then we also have a really handy save to GitHub feature off to the right if you wanted to save to a public or a private repo. All of these things are kind of generating prompts on the fly. So if you need to have a specific prompt to engage with the model as part of the app, you can. It's handling all of these services like the webcam. If it encounters any errors, it will take the error, feed it back into the model, and then use Gemini in order to resolve it. And at the end of this, we should be able to deploy to Cloud Run as well. This is all part of an improved code generation and vibe coding experience with our latest Gemini models. They've been topping all of the leaderboards, including LM Arena, for these code generation scenarios, and it's been really exciting to see how they've improved over time. So let's try and see if this works. I'm going to begin the quest. This does hopefully look okay. So it's consulting the ancient tomes, rolling the dice of destiny. Powered by Gemini, unleash your imagination. So let's also zoom out a little bit so we can see the full app. Bargaining with a mischievous fae. Oh, that sounds very cute. And then that does look very much like me. Well, in my dreams, right? But it does have kind of the original portrait. Neutral good, bard, I'm an entertainer. Well, that's nice to say. Warm smile and gesture of peace. And then you can see the character backstory along the way. I actually really love this and think that this should probably be my Facebook image. But Lyra, bright song. So cool enough, if you select a Google Cloud project, I'm just going to hit this one. It verifies the project, and then you can click Deploy App. It creates a unique URL behind the scenes that you can share with your friends, your family, other folks that you want to join your D&D campaign. And then after this is created, so you can see the app, it gets deployed. But even cooler, you can also take a look at all of the logs, the Google Cloud kind of services that have been created along the way. And all of these things are kind of scaled out to production. We care about the headaches of Kubernetes and the like, so you don't really have to. You can also see billing associated with that account. So if I pull up the billing for my linked account, which is where all of the apps that I've deployed are getting utilized, you can see that clearly I have a problem, but also that there are a lot of Gemini APIs, Cloud Run, and cloud storage components just kind of added behind the scenes, so I don't have to worry. Another cool feature that I mentioned, my colleague Guillaume shared a little bit earlier today, is the live feature. So I'm going to go ahead and click Stream. You can add to the system instructions, so you can say something to the effect of, please only speak to the user in French, and kind of have that added. And then you can do all sorts of things. You can share your screen, you can share a video feed, and the model kind of interacts with you dynamically using the languages that you specify, or using a variety of languages based on the user conversation. I'm going to go ahead and ground with Google Search, and then I'm going to go ahead and share my screen and ask Gemini what it sees. And I've already got kind of pulled up into a tab Google Colab. Do not judge me by the number of untitled notebooks that I have, but I'm going to go ahead and ask Gemini what it sees. Hey there, Gemini, what do you see on the screen?
Je vois une interface de notebook Python dans un environnement de développement en ligne. On dirait une version de Google Colab. Il y a un champ de saisie de code avec un message qui dit « Start coding or generate with AI ». Que voudrais-tu faire avec ça?
Was that correct? Okay, cool, excellent, good job, excellent. More cheers. But even cooler, you can also ask for help with the UI. So you could say something to the effect of, "Hey Gemini, how would I change the runtime type in this Colab notebook?"
Pour changer le type d'exécution dans ce notebook Colab, tu dois cliquer sur le menu Runtime en haut de l'écran, puis choisir l'option Change Runtime Type. Là, tu pourras sélectionner le type d'exécution que tu souhaites parmi les options disponibles. Est-ce que tu as trouvé le menu?
Awesome. So it was able to kind of navigate me through the UI, tell me what to select, and since I've turned on Google Search grounding, I can even ask, "Hey Gemini, is it going to be raining in Paris today? Like, what is the weather like in Paris?"
Excusez-moi, je n'ai pas bien entendu. Pourriez-vous répéter votre question sur la météo à Paris?
Yeah, so it was asking, it sounded like it didn't get it right, but it does have the ability to look up information on Google Search, so you can ask it natural language questions, even specify your own function calls, and the model should be able to kind of pull in that information. In addition to all of this kind of operating within Google AI Studio, again, if you click Get Code, you get everything that you need in order to replicate the experiment. We've also been baking Gemini into Google Colab itself. So one feature that feels very underloved and underutilized, at least to me, who really enjoys working with data, is that you can specify a different data set. So I'm going to copy the path to this CSV file, which you can just kind of see here on the left. You can also add a link to a URL and ask for Gemini to help with web scraping it. But you can say something to the effect of, "Please do exploratory data analysis," if I could type, "on this CSV file and build a model to predict California housing prices," which is always like a very depressing thing. But kind of similar to what we just saw in Google AI Studio, what happens behind the scenes is that Gemini builds a plan. So it kind of creates step-by-step instructions for what it would need in order to accomplish the task. So you can see here, loading data, kind of doing EDA, feature engineering, data preprocessing, model selection, and all of that kind of gets incorporated into the step-by-step process. And then Gemini writes the code and executes it within the context of the notebook. So if you've never used Colab before, this is kind of a notebook-based interface on top of some compute with a whole bunch of Python libraries installed. What's happening is that Gemini is doing each one of these tasks. It's describing its reasoning. It's writing the code. It's executing the code. It's using the outputs for each of the cells that it's created to kind of inform the next steps that it uses for its analysis. So it's analyzing these data. It's creating these really rich, detailed plots for the CSV file, but it could also be JSON, it could be TSVs, it could be like a table that you're importing from a database or from BigQuery. It's doing feature engineering. It's deciding based on the structure and the shape of the data what kind of model it should be using to train. And then afterwards, it's giving you kind of a summary of the results and explaining all of its reasoning traces along the way. So this is pretty cool. I started doing machine learning back in 2009, like back before scikit-learn even found its legs. And it's been really, really just brain-boggling to me to see how all of these tools have evolved over the context of the last year or so. And so it looks like it's decided to create a linear regression model. It's training the model, and then it should give us some sort of insight into into kind of the results that it found for the data set and the R-squared values. So you see MSE, R-squared, and then hopefully a summary of all of the results at the very, very end. So this is pretty cool. I highly encourage everyone to play with these features, these agents that are baked into Google Colab, the features that are baked into AI Studio, the models that we have available, and to test them out for all of your use cases. But in the interest of time, I'm going to go ahead and go back to our original presentation, and we're going to careen along the way for the rest of the examples. So VO3, hopefully everybody is excited about VO3. VO3 is one of 3 of our generative models that have been released into the public. Imagine 4 is for image generation, Lyria for music generation. But given that no AIE presentation is complete without a quote from Andrej Karpathy, I'm really excited about video in particular because it's an incredible medium to kind of help educate, but also to help communicate, especially for audiences that are like my niece and nephew's age. You know, they already tell me Paige, nobody reads anymore. But I think video is something that can resonate and really find places with people who have different learning styles, with people who maybe don't want to take the time to kind of learn through alternative means. And so VO3 is kind of the first step in the path of making that a reality. So in the interest of not cycling through all of the text on this screen, I'm going to do a lot of showing. So we've got a lot of new features as part of our VO models, one of which is kind of this character consistency or reference-powered video. So here you see a person and a hallway that have both been incorporated into kind of the prompt for the VO model. This is still using VO2. But then you see kind of that same character walking down the hall as you describe. Reference-powered video, very similar. You can have the same character just in a variety of scenes, a variety of lighting cases, and it still looks like the same happy little monster kind of swimming or walking or hanging out at a gas station. We also have a feature where you can take in an image and animate it. A feature where you can have an image with a guide for the animation, so not just kind of like creating what it looks like might happen as the next step, but actually nudging it to be like a woman walking down the road in Texas. You can have these sort of camera controls where you can control the style of the video outputs, outpainting, which was really, really important for a recent exploration that DeepMind did to kind of restore the Wizard of Oz into a state such that it could be displayed on the Sphere in Las Vegas. Adding objects to scenes, removing objects, playing around with perspectives and camera controls. There's just an example of removing objects. You can do the same with our Nano Banana models. by the way. You can have reference face movements, so an avatar and kind of reference face movements that control it. First and last frame, so you can define the first frame, the last frame, and ask for the VO models to interpolate between it. And then, again, all of that possible with our last iteration of VO models. VO3 kind of takes it to the next level. So with VO3, you can do things like have photorealistic video of people and places. So these were all created just through prompts and just through prompts coupled with input images. Hopefully you can hear the audio also displayed in the room. But these are everything from kind of these futuristic landscapes to things that feel a little bit like a scene from perhaps Lord of the Rings, where before Frodo throws in the ring into Mordor. But lots and lots of cool things to do with VO. Again, in the interest of time, I'm going to show you just one more video to kind of get the gist of what's possible, created by our friends in the Google Paris office. Yeah. It's like Daft Punk.
I can't believe this new VO model. It is amazing.
Ah, yeah, je comprends pas ce que vous dites parce que je suis français en fait.
Intelligence artificielle! Intelligence artificielle! Est-ce que j'ai une gueule d'intelligence artificielle?
C'était un bon modèle VO?
Vous savez, moi je ne crois pas qu'il y ait de bons ou de mauvais modèles de génération de vidéos.
Alors que penser jusqu'à présent de ce championnat des intelligences artificielles?
Je pense que la stratégie de l'entraîneur est bonne, tant sur le plan technique que tactique, mais l'important c'est les VO 3.0.
Boss, les humains sont sur le point de créer l'AGI, doit-on les contacter?
Qu'est-ce qu'ils en font?
Ils génèrent des images de starter pack et font des montages vidéo stupides.
Ils ne sont pas encore prêts.
VO can make us sing anything.
Awesome. So if you see M. Blanc anywhere around the Google Paris offices, definitely tell him that he has an excellent taste for filmmaking. So moving along to the next slide, or attempting to move along to the next slide. Yep. So one of the things that I wanted to try with the VO3 model when it was first released was to see if I could create or really replicate a commercial that I had seen on television. I wanted to see how much easier it would be to do with VO3 versus VO2, and also how many other models I would need to stitch together in order to make that possible. So this is the advertisement in question.
Hey, my name's Paige, and what makes the Chick-fil-A chicken sandwich original to me is the crispiness of the breading and the tenderness of the filet. It's tasty, it's warm, it's total satisfaction.
So that's not me, Paige. That's like some other Paige that also likes chicken sandwiches. But the kind of the next step to kind of build a similar style of experience with VO2 is I take the original image, I give it to Gemini 2.5 Pro, I asked it to segment it into 8-second clips, generate a unique prompt for each 8-second clip. That was all used to kind of guide and steer the VO2 outputs, which again, as a reminder, don't have audio. So to have audio incorporated, I used the text-to-speech version of Gemini in order to create the audio track. I used kind of a music model to generate a 30-second clip for the audio in the background, which I also used Gemini 2.5 Pro to describe. I stitched it all together using Camtasia, though you could also use MoviePie, and then I got that final video, and it looked a little bit like this.
Hey, my name's Paige, and what makes a Chick-fil-A chicken sandwich original to me is the crispiness of the breading and the tenderness of the filet. It's tasty, it's warm, it's total satisfaction.
And I actually kind of like this one better. It's a lot more chill. But again, this is using VO2, a collection of models. Took about 25, 30 minutes in order to create end-to-end, which is still a lot less than it would have taken for kind of a professional movie making team, I think. But one of my colleagues also told me that clearly it was wrong because like the breading on that chicken was like completely different than Chick-fil-A breading. It was definitely Popeye's breading. Like some work to be done. But with VO3, the process is much simpler, as you can see. So you just have the original video. You ask Gemini 2.5 Pro to create the prompt or the collection of prompts. In this case, I only wanted the first 8 seconds. It generated the detailed text description, and then that's what I used to kind of give to the VO model to get that final output. And so this is what it had.
Hey, my name's Paige, and what makes the Chick-fil-A chicken sandwich original to me is the crispiness of the breading and the tenderness of the filet.
And so that's pretty strong with just a single prompt. Genie 3 is our new frontier model for kind of exploring worlds. You can navigate just with the arrow keys. Behind the scenes, it's powered by techniques similar to our VO models, as well as a lot of integrations with Gemini. So it's kind of a harness style approach for generating these worlds and allowing you to navigate through them. But you can just create via a prompt or via an input image the kind of worlds that you would like to see, navigate through them. And there's even consistency. So if you interact with the world, if you draw something on the wall, if you look down and you see that your galoshes are yellow, it will remember that and persist it through the duration of the exploration. You can even see what it would feel like to experience a hurricane in Florida from a road, which is pretty rad. We should be having a trusted tester program for it coming pretty soon, but stay tuned and can't wait to get that out to folks. So we've talked about a variety of models, Pro, Flash, Flashlight, and I also want to talk a little bit about our Nano model family, which is small enough to fit on mobile devices and to be embedded within browsers. Specifically Gemini Nano, and then also some of our other open models like Gemma 3 and 3N. So interestingly, for Gemma 3, how many folks have used Gemma 3 or heard about it? Gemma 3 is remarkable in a few ways, right? Like, so you can see here that our 27 billion parameter version of Gemma 3 is kind of able to fit on just a single H100. So just one GPU as opposed to the 32 that you would need to run DeepSeek R1 or DeepSeek V3. And even cooler, Gemma 3N, which is 4 billion parameters in size. So small enough to fit on your laptop, like small enough to be, locally hosted. It's free to use because you can download the weights. It's actually exceeding the capabilities of our Gemini 1.5 Pro model, which was our best model, 6 or 7 months ago. So I just want to underscore that, right? Like our best model, the one that took multiple TPUs to run, is now, being bested by an open model that is small enough to fit on your laptop and that you can use for free. So if you fast forward 6 months from now, right? And you look at the frontier, what's possible today. So Genie 3, VO3, Nano Banana, all this cool stuff. You could easily imagine that probably all of those models or equivalents would be friendly enough to run on your local devices without you having to send data anywhere, without you having to send something to a server. And also the frontier would probably look dramatically different than it does today. So I truly think that open models and locally hosted models are the future. And we're deeply, deeply investing in that, not just for Gemini on Pixel devices with Gemini Nano, but also something called Gemini in Chrome. We announced this about 5 days ago, but with Gemini in Chrome, you can do a variety of things. You can summarize information across tabs, and coming soon is a feature that feels very similar to Project Mariner, if you've seen that before, but it allows you to kind of ask in natural language, hey, here's an email with a request for me to make something. Go on Instacart or go order me all of the groceries and put them into my grocery cart and check out, please. And all of this would be available, embedded within the browser, and just kind of free for you to use or to interact with as part of your Chrome native experience. So this is, it feels very futuristic. It feels like sci-fi, but it's stuff that is definitely coming down the pipe from Google's perspective. I also want to underscore there has never been a better time to be a founder. So if any of you in this room are startup curious, there's almost nothing stopping you from creating a company that's cash flow positive and getting it out into the world. We've also seen a whole bunch of VCs that we partner with founding or not founding, but supporting solo founders much more than they have previously. So if you've always felt a little bit unsure just because you wanted to build a business, but you didn't necessarily have a partner, again, never been a better time. Smaller teams also capable of doing outsized amounts of work. Like if you talk to the Black Forest Labs guys or the Mistral guys, it still boggles my brain how much they're able to do with just a relatively small number of engineers. So I just want to encourage you, if you need any encouragement, to go build, go create, get things out into the world. With that, hopefully I didn't go too much over time, but I wanted to just say thank you. Thank you so much for having us. And thank you for all your great questions, for sharing your use cases. We're really excited to see what you are about to build and have been building with the Google DeepMind models. And your homework for today, if you haven't already tried it, is to go to ai.dev and start experimenting with Gemini, generate an API key, and start using it in your projects. So thank you so much. Thank you to the team from DeepMind who is here today that has been doing all of this work. And we appreciate you.
Thank you, Paige. That was amazing.
Yeah. Excellent. Do we have time for questions?
Yes, I have a few follow-up questions for you.
Excellent. And it's okay if they are spicy. We can talk spicy questions.
Let me think now.
All right.
All right, they're not that spicy, but I think so. Amazing presentation.
Yep.
I'm like the mind-blown emoji all over. Well, I was blown away. I am speechless now.
Yeah.
I've seen you use VO2 instead of VO3.
Yep.
I know that you said VO3 is VO2 but supercharged.
Yep.
But are there like real use cases for VO2 now, even if VO3 is available?
There are some features that are still only available via the VO2 APIs, but we're quickly trying to integrate them with VO3. So hopefully in the future, there won't be a need to rely on the VO2 models. You can just use VO3 natively. From a pricing perspective, we're also bringing down the costs of VO3 pretty significantly. They've already dropped over the last month or two. So like definitely, if you're thinking about building something or creating video, like prioritize VO3 explorations compared to VO2.
Awesome. Yeah, you spoke about so many models and you mentioned Jain 3.
Yep.
And I was wondering how much of Jain 3 was actually used for autonomous vehicles and to train autonomous robots as well.
Gotcha. So the Genie 3 models, I don't think that they've necessarily been generating data to be training autonomous vehicles at the moment. But we do include synthetic data into pre-training and post-training for the Gemini family of models. So I'm sure that folks have played video games before, or if you haven't, like, live a little, like there are a lot of really cool games out there. But like a lot of the footage of agents interacting in video games, kind of accomplishing tasks, exploring the world, are also really useful training data for models such as world models or even models like VO3 or Gemini's sort of video understanding capabilities. So I definitely think that those kinds of data would be really, really interesting for models to incorporate back. But even just kind of the agents exploring world-style video game video footage is really, really helpful for model training too.
Very cool. I have one last question for you.
Yep.
So
just one?
I have so many written down, but yeah, for the sake of time, I can only have this one. But I think I'll catch you later for sure. So what's unique about DeepMind's models, and what are you excited about?
Yeah, so DeepMind's models, I really, really love how we're kind of pushing the boundaries for multimodal outputs, the audio outputs, the video outputs, but also, open source is kind of near and dear to all of our hearts, I think. The Gemma team is doing phenomenal work. And I really have been excited to see how these smaller models can be incorporated into, things like Chrome and to mobile devices. And really can't wait to see more of the roadmap of Gemini and Chrome. I think it's truly magical to kind of imagine this world where you can, have all of your data kept local, but it can accomplish a variety of tasks for you, or can toggle efficiently between models that are zero cost because they're just running on local devices, and then models that need to be used that might be hosted server side.
Wow. Well, thank you so much.
Yep.
Thanks, Paige. You guys have been cooking for sure. Shipping every 5 days is incredible.
Well, everybody on the team has been contributing. Like, it's been fantastic to get to work with everyone, and I feel fortunate and honored to go to work every single day. Yeah.
Thank you so much.
Excellent. Thank you.
Give it up for Paige.
Yeah.
All right. Time to announce our last speaker of the day. Up next, our speaker led generative audio research at Google Brain and earlier worked at the speech recognition at Facebook AI Research before he co-founded Qt, where he serves now as Chief Modeling Officer. Today, he'll talk about full duplex conversation with Moshi, speech-to-speech with Hibiki, and more. Please join me in welcoming to the stage Chief Modeling Officer Neil Zegedor.
Hi everyone, thanks a lot for having me today. I'm happy to talk about our work on scaling real-time voice AI. And before that, I would like to say a few words about Qt. So Qt is a non-profit AI research lab we created in Paris 2 years ago. So thanks to the generous donation from Xavier Niel, Rodolphe Saadé, and Eric Schmidt. It's an AI lab that is focused on open research and open science. So the main mission is to make big advances in AI, in particular around multimodal LLMs. And the specific thing about Qt is that since it's a non-profit, all our inventions are published, shared in open source. We train PhD students, we collaborate with academia, and so on and so forth. And so, what do I mean by scaling real-time audio? So you may be familiar with solutions. There are a lot of them around, like 11 Labs, Azure, and so on. And so currently, the main applications in AI voice are around offline content. So typically, you will generate an audiobook with a synthetic voice, or you would have a character in a movie that could say a few artificial sentences, or a small character that can in a video game also interact with you, and so on and so forth. So this is mostly offline content. So this is content that is highly qualitative and is generated as low volumes. A huge opportunity that is currently not really addressed is everything that is interactive and very high volume. So taking again the example of the difference between live content and the rest, when you make an audiobook, you can pay a lot, you can spend a lot of time iterating because you generate it once and it's consumed by a lot of people. On the other hand, there is a lot of content that is generated on the fly and needs to be processed right now and is consumed by a few people and then thrown in the trash. So for example, if you look at gaming, if you have interactive NPCs with whom you're going to talk, these interactions, there will be a lot of them, they are heard by a single person, and so they need to be very, very scalable, right? It's the same for robotics. Eventually, humanoid robots are going to play a huge part in our society, and interaction with them will be mostly vocal, right? So we're talking about lots and lots of volumes of audio, much more speech, AI speech than is currently existing. Same for media. Audiobook is massive media where you generate one audio for a lot of people. But now, when I show some examples, something that is starting to be a new product is personalized news, where you have your own news. Instead of consuming the same as everyone, you have some personalized news digest about your interest. It's the same. In that context, this is very focused on a single person, so you need to generate massive volumes of audio. And what does we look for when we mean voice AI? So the first thing is the kind of applications we are interested in. So people will naturally think about speech synthesis or voice agents, but there are a lot of things you can do. So synthesis is a task of you give a text and it generates the corresponding audio. Transcription is the fact of, on the other hand, writing what is being said. It's very useful, for example, for meetings and so on. Translation is translating speech in another language, most like hopefully in real time, conserving the voice and so on. Transformation is all the kind of audio effects you can do on a voice. So if you look, for example, at visual effects, in even apps like TikTok, Snap, and so on, there is a lot of AI in it, right? So you can make a lot of AI-based transformation on your face. But the audio effects is like pitch up, pitch down, slow, faster. You know, it's not really using AI right now. So you could imagine much more richer transformation. And the last one is the full conversational experience, the voice agent. So now, when you have this set of capabilities, what are you looking for in terms of quality? First one is fidelity, right? So it needs to sound like if it was recorded in a studio and not on a smartphone in the subway. The second thing is you want to be able to design voices, either by cloning them or by writing natural language description, like I want a middle-aged man who smokes way too much and has a deep voice or something like that. You want emotions to be rightfully understood by the AI and also be produced consistently. So right now, you may be crying with your AI voice, and it's going to be like, oh, that's so great, and so on. So, you know, it's not really exactly the kind of interaction you are looking for. The flow should be very natural. Right now, and I talk a bit about it, you need a lot of discipline when you talk to an AI, and so you'd rather want to have something that is, you know, much more natural, like a human conversation. Finally, the latency needs to be very, very low. And now about scalability, I think the two main challenges we are facing right now, and Paige say a few words about on-device models, sorry. If we want to scale audio generation to reach all the use cases I showed before in gaming, assistance, personalized media, and so on, either we need to be able to generate very large-scale volumes on the cloud, or we need to be able to have small-scale generation on device, right? So let's say you want to make an NPC in a video game. Either it's hosted on the cloud, and you need to generate millions of hours of NPC voices, you know, every month or so, or everybody is running on their PS5, the local TTS device, and so in that case, it's scaling through devices, right? So in particular, if you look at quality and scalability, there is kind of a trade-off where people currently have to choose. So if we take speech synthesis, again, very high quality, low scalability, the audiobook, right? You generate it once, it needs to sound very good, but you don't need to generate a lot of them, right? You make the Harry Potter's books, and you sell them, and you make a lot of money. On the other hand, voicemail requires a lot of scalability because everyone has their own voicemail. It's a interaction that you cannot predict, so it needs to be generated for everyone. But the quality can be pretty crap, right? If you call your voicemail, you don't need a full emotional understanding. You just want to know what people wanted to tell you. At the intersection of quality and scalability, there is a personal assistant. Now the content is not mass media. Everybody wants to have their own interaction, but they want it to be as qualitative as if it was the premium audiobook. So in that case, you need to nail both aspects at the same time. It's the same for translation. If you do diplomatic interpretation, really not our focus right now, because the expectations on reliability and accuracy are extremely high. Same if you are asked by, I don't know, Netflix to dub a movie, the expectations on the quality are going to be very, very, very high. On the other hand, if you're translating, you want to be translated while you travel, it's a bit related to the recent release in the AirPods Pro. Then it's okay, I guess, if the quality is a bit lower, as long as it's useful and kind of reliable, and in particular can run on device so you can bring it with you in your travels. And at the intersections of quality and scalability, you have meetings, phone calls, or small creators. So small creators is a bit like in opposition to movies. So in the case of movies, you make one movie for a lot of people. For small creators, the content is consumed by a few people, but there is a lot of content that is generated at the same time. So you need to translate much, much more content. Finally, for voice agents, one example I like is a startup working on airline claims. So if you do airline claims, it's like an AI that calls the airline and say, yeah, the flight was late by 1 hour, so you need to give us $300. In that context, if you pay $10 for the voice, it's fine, right? Because you get a lot of money. But now, if you have a bot at McDonald's that wants to take your order, it needs to be super cheap. But at the same time, the quality can be pretty crap as long as it takes the command right. And at the intersection, you have video game NPCs, interactive podcasts, e-learning. So if you want to learn a language through voice, not only it needs to be very cheap for you, because you don't want to spend like $500 a month to talk to it, but also you want the experience to be enjoyable and to be qualitative and so on. So you need to nail both aspects at the same time. So what I'm going to show is how you can address all these aspects and the story at Qt around them. So the first one is about quality. So the first project we did at Qt, called Moshi, it was about creating the first full duplex conversational AI. It was more than a year ago, before the release of the advanced voice mode from OpenAI. Now it's something that people are used to have, conversational chatbots. All of them without exception, even today, still rely on a half duplex setting. It's a bit like a talkie-walkie. So either the AI is speaking or it's listening, which means that it requires this discipline. So it's always a bit awkward when you talk to an AI, because if you interrupt it or you cough, it thinks you are interrupting, and so it starts breaking the flow of conversation, and so on and so forth. So it's not very natural, because you need to adapt to the limitations of the voice, rather than the voice adapting to the fact that, I don't know, maybe you are erratic in the way you speak. Full duplex is the fact that the model always speaks and always listens. It can interject at any time. It can be interrupted at any time, exactly like in a human conversation. In a human conversation, if you're on the phone with a relative from your family, the amount of overlap speech is around 20%, which means that 20% of the time, people are speaking on one another, and that makes it, like a rich conversation in a way. And so how do we address that? That's a small technical part in this talk. We wanted also to address another aspect, which is that people rely on cascaded systems. So typical chatbot is speech-to-text, and then you have an LLM, and then you have text-to-speech. How can we merge all these steps into a single one? Because if we merge them into a single one, we don't lose emotional information, because we don't go through text, and the latency is going to be much better. So the way we did it is by taking inspiration from text models. So very quickly, a text model, text LLM, is a probabilistic model where you give a sequence of words and predict the next one. So Qt is you predict AI, and then you inject AI and predict research, and so on and so forth. So our main algorithm and the expertise of Qt is audio language models. How do you make an audio language model? The most basic thing you could do is say, OK, I'm going to put audio as input and audio as output of the LLM. It doesn't work at all for a very simple reason. Look at the sentence. Qt is an AI lab based in Paris. It's 8 words. So if you want to pass it into an LLM, it's very few tokens. It's around 3 seconds to pronounce this sentence. Even at 24 kilohertz, which is not studio quality audio, you get 72,000 values, which means that you have a super long sequence to pass through your LLM. And given that self-attention has a quadratic cost, so it's proportional to the square of the length of the sequence, it means that it's 100 million times more costly to process audio than text with an LLM. So what we did instead is that we invented Mimi. It's a codec. It's like an alternative to MP3 or Opus. It takes a large audio file, and it compresses it so densely that it's a bit like a text representation. In the case of the sentence I showed, instead of having 72,000 samples, you go to 37 tokens. So now, it's almost as if it was text. And you can just train an LLM to predict these tokens. Then your LLM predicts these audio tokens, and you have a decoder. It's a generative adversarial network, and it's going to reconstruct high-quality audio from it. So now we have turned the task of audio generation into a task of language modeling. And in particular, that's the main standard architecture used by Google, OpenAI, and so on for modeling conversations. And the way they do it is that they have an audio LLM, and they have this sequence of audio tokens that either represents the LLM or the user. So in that context, the model is going to predict the next turn based on the previous turn. It works nicely and can give all the chatbots that you have right now. But it's still a talkie-walkie, because it's either the model is speaking or the person is speaking. So what we did is we invented what we call multi-stream modeling. It's a very simple idea. We just have 2 streams in parallel, which means that both can be speaking at the same time, both can be silent at the same time. One can talk and the other around. And what it gives, and I'm going to show you, it's a demo we did more than a year ago now at IRCAM. You're going to see 2 things. The first thing is conversation with Moshi, where you're going to see that the model has still the lowest latency ever at this point. Sometimes when it guesses where you're going, it starts answering before you're done. You're going to see Alex speaks at the same time, and there is no problem with this ambiguity where both are talking at the same time. And the second video, it's me during work in our office, where it's super noisy, and it's good advantage of full duplex models, is that since they don't have this awkward handling of speaker turns, you can have a lot of background noise and they just work pretty well.
So the planet is Sirius 22. Can you plot a trajectory course to it, please?
Yes, sir.
Okay. How long is it going to take us to get there?
I've mapped it out.
Okay.
It's approximately 5 months to get there.
Okay, that's not too bad. Do you think we have all we need on board the ship to start the mission?
Yes, sir. We have everything we need.
Okay.
Good day. How are you doing?
Hey, I'm doing some construction work right now, as you can see. I'm looking for some advice. Can you help me with that?
Sure. I'm happy to help. What's the issue you're facing with your project?
So in that context, I couldn't even hear anything, and the model has no issue handling noise. The second thing we tackled is capability. So the multi-stream architecture we invented is not an architecture only for dialogue. It's basically a general framework for modeling any kind of audio task. In particular, if you take your two streams and instead of having the LLM speak and the user speech, you can have me speaking in French and me speaking in English. And now you can predict me speaking in English from me speaking French, and you get real-time speech-to-speech translation.
Bonjour à tous. Je suis ravi de pouvoir m'adresser à vous aujourd'hui en français.
Hi everyone, I'm delighted to be able to speak to you today in French since my phone will translate what I am telling you into English. As you can see, it is in airplane mode. It doesn't have an internet connection because our machine translation model allows for real-time voice translation entirely on the phone. You can find the model for free download on Hugging Face.
So in this context, this model was made by a single master intern in a few months because since it's the same architecture, just generate new training data, it's very easy to go from conversation to translation. It's again extremely robust to noise.
My name is Alexandru, and I am testing this model in extreme conditions. At this moment, there is very loud music, and I can barely hear what I'm saying. However, our model is able to translate live.
So it's Kavinsky behind. You cannot probably recognize him, but anyway. So this is for translation. Again, you can... There is a live demo coming and everything can go wrong, so please bear with me. From translation to transcription now. So, okay, I showed two tasks. Now, instead of predicting English from French, you can predict text from speech. And in that context, basically, the idea is the following. So it's still the same architecture. But now what it can do is real-time transcription. So at the moment, it's the most accurate and fastest real-time transcription in the world. It's open source. And the way it works is it predicts in a continuous fashion the text from the speech. And so this, par ailleurs, ça marche aussi en français. Ça supporte ce qu'on appelle le code switching. Donc vous pouvez parler dans les deux langues et puis ça va bien retranscrire. And now I can go back to English and it's going to work, hopefully, I hope so. Okay, first demo, okay. Back to the presentation now. You can also do it the other way around. So instead of predicting speech from speech, you can predict speech from text. So it's, in that case, streaming text-to-speech. So text-to-speech, there are a lot of them out there. The specificity about this one is that it's streaming on text, which means that as you type words, they start being generated. It's useless for a human because it will be super weird for typing and start speaking. But when you want to make it work with an LLM, it's very useful that, let's say you want to make a conversational agent from an LLM, and the LLM is going to produce a huge paragraph. You don't want to wait for the LLM predicting the paragraph to start predicting the audio. You want both to be predicted at the same time. So in that context, what you're going to see is the actual real-time latency.
Coming up next, we've got something special, the AI Engineer Paris after party. Enjoy drinks and fruitful conversations. See you next time.
Please stay. It's not. I should have put it at the end of the presentation. So it's not. It's not. Please, a few minutes more, and we can have some drinks. And interestingly, so there was a nice talk earlier by our friends at Pioneer. But again, instead of predicting just text, you can also predict text with the label of who is speaking when. So if you have a meeting with a lot of people, you want to be able not only to transcribe a single stream of text, like is often done, because it's hard to parse, but rather having the model detect who is speaking and associating the right transcript to them, all of this still in real time.
Understand that? Yes. Okay, I tell you, if you need to tell me something, I'll let you come up here to the podium so you can speak into the microphone and I can hear you.
Yes, the attorney here, I'm wanting to fire him.
Uh-huh.
And, I don't feel like he's doing any...
Who are you going to hire?
I'm not going to hire nobody. I'm going to try to get a different public defender.
There isn't... You have a right to an attorney.
Yeah, anyway, so, I don't want to put too much content because otherwise it's going to be strike. But anyway, so that shows the flexibility of this model. And now, what you can do is you take the real-time speech-to-text and a real-time text-to-speech, and you can put an LLM in the beginning. So in a way, we are back to what I showed before, which is the cascaded system. So it has more latency, and it's not speech-to-speech, but the very nice thing about that is that it's completely customizable. So you don't have to touch the LLM. So you have a LLM with like a vision, understanding, and function calling, and tool use, RAG, whatever you name it. Most people, they just want to make it speak. They don't want to train a new model that is completely replacing their text stack. So in that context, and that's going to be the demo that worked perfectly during the rehearsal and started freaking out 30 minutes ago, so let's see. In that context, the way it works is, for example, I can put upload a 10-second sample. So in that context, I uploaded a voice sample from Général Charles de Gaulle, from l'appel du 10 juin. And I write a personality to the LLM, so just a prompt explaining that I'm talking to Général de Gaulle. And now you can have like design with a 10-second sample and a very short text, a new conversational experience, basically.
Je suis Charles de Gaulle, général de la France libre. Je suis ici pour partager avec vous des moments historiques et des réflexions solennelles.
Bonjour, mon général. Est-ce que vous m'entendez?
Oui, je vous entends parfaitement. C'est un honneur
Excuse me,
de converser.
my general, for the sake of the audience who is mostly English speaking, maybe you can switch to English. So right now I'm giving a talk on audio language models, and I was thinking maybe you could have some advice for me. Maybe you could try explaining it in your own words.
Ah, bien sûr. When I think of language models, I am reminded of the importance of communication during the darkest days of World War II. We had to convey messages clearly and with conviction to unite the French people. In the same way, these models must be precise
Okay,
and
thanks
compelling.
a lot, my general. Thanks a lot.
Let's
Have a
find
good
out.
one. And so finally, the last one is about scalability. So the demo I showed of the on-device speech-to-speech translation, you can also run it on the cloud, and on a single H100, you can process 320 concurrent conversations. That means that on a single GPU, you can serve hundreds of concurrent conversations. Similarly, if we look at our speech-to-text and text-to-speech, so our text-to-speech in terms of streaming solutions is more accurate than Whisper, for example. And the throughput, it's the number of seconds you can process in 1 second, right? That means that we have like a 400 times real-time factor against a 5 times real-time factor for Whisper streaming. Same for our TTS, that is open source. If we compare to the main open source TTS, Orpheus, Dia, CSM, Chatterbox, we have more than 100 times higher throughput, while having a smaller word error rate, which means that we have better pronunciation and fewer errors. What that means is that now you have something that can scale to address all the applications that I've started describing. Because now if you want to make NPCs in video games where everybody is going to have 20 villagers they can talk to in a huge open world and so on, it starts to become believable, which was really not the case until now. And to give you a final idea of just a final demonstration of this, you can, as of today, on La Provence, listen to a news article with our voice.
De l'offensive israélienne à Gaza.
Ce mercredi 24 septembre, des dizaines de Palestiniens ont été...
So, yeah, probably not the best topic, I really apologize about that. But here what you see is the difference between two types of media. What I just played is the journal for everyone, right? So that's kind of the audiobook. It's a single media generated for everyone. On the right, unfortunately, it's not available on the web yet, it's on the app. It's a personalized news digest. So in that context, there is only a solution like ours that can scale to generate for each person reading a journal their own news stream. So basically, our goal is to go and remove the trade-off between quality and scalability and provide both. And in particular, what we have been doing with La Provence for incorporating our models into products is the kind of collaborations we are as well looking for right now. So you can find all our code on GitHub, our pre-trained models on Hugging Face. We publish all our research on archive and in conferences. So all of this can be found. And we are interested maybe in opening limited access to an API that we can serve to people who want to try to prototype large-scale audio generation. So what we're excited about is if someone wants to make a video game with NPCs, with voice, or someone wants to automate customer support for something, or create an education app, and so on, super interested in this kind of use cases, so please don't hesitate to reach out. This link brings to a Google form where you can reach out to us. Thanks a lot for your interest. Thanks a lot for bearing with me. Yeah, Thanks for your attention.
Wow. Thanks, Neil. Thank you, Neil. Would like to join me for a couple of questions? Awesome. All right. There's so much to unpack there. All right, so yeah, you showed multiple models. I don't know where to start from, but what's the most challenging part of developing a model like a full duplex model?
So the reason why we did the full duplex model is, so when we started working on it was early 2024, and dialogue at this time was really the task that nobody had been able to tackle at all, right? TTA started to work. We had done at Google, I had worked on music generation and so on. So all of this was kind of working well, and there was really nothing for dialogue. So at Qt, our strategy is always the same, right? We are a small lab, a small team. So what we try to target as projects are things that are very new and can be tackled by a deep expertise of the topic rather than scaling a lot the resources and so on. So what is the most challenging is that, in particular, and I really love it about audio models are typically very small. They are around 1 to 3 billion parameters. So it's not about scaling huge infrastructure and so on. It's really about understanding how the human hearing works, how speech production works, how you can put that knowledge into machines. And so it's really about having a very deep knowledge and interest of the field of audio, rather than just a general knowledge of machine learning, I would say.
All right, very cool. Yeah, you mentioned that you have a small team, but Qt is also non-profit. So
yes.
Can you expand a little bit about that?
So the reason why we created Qt as a non-profit is, so the ambition is to create something that can foster new ideas that are groundbreaking. And what is interesting is that if you look at the main inventions in AI, for example, one that is transformer, right? The transformer architecture that was invented at Google. It was invented with a specific application in mind, which is machine translation, but it was invented at Google Brain, the fundamental research lab. And the reason why it's so is because it was a complete rethinking of the way you do sequence modeling. People were using recurrent neural networks. There is no relation between recurrent neural networks and transformers, which means that you really need to be ready to say, okay, let's think everything from first principles.
Right.
Maybe we can waste a year, but if it works out, it's going to be huge. It's very hard to do that in a startup, so we decided to do a non-profit because we really wanted to have a mission where we can try stuff, fail, and just focus on making big things without having distractions. And Xavier Niel, Eric Schmidt, and Rodolphe Sade were very happy to accompany us with that.
That's very cool, but you still have some commercial partnerships as well, right?
So we start getting interested in that with the main reason of, as I showed you in the benchmarks, we are a non-profit, and at the same time we make research models and realize they are very competitive to the point where they can be competitive with commercial solutions. And so we'll be interested in providing them to people not only through open source models, but as well specific models that where, let's say, someone needs a model in a specific language, and they are okay to open source it, and they want us to work on it. Obviously, we need to find a way to make it work because we are a small team, but we are very happy that our open source models can also be used in products.
Awesome. So what's next for Qt, and what are you excited about?
So what we are excited about, in a way, and I think it's quite interesting, is so Moshi was the first full duplex model, and then Unmute, what I showed with General de Gaulle, is a cascaded model. And all the field seems to go back to cascaded model because it's just so much simpler and more convenient for products. Which means that the progress for full duplex model has kind of remained almost flat since Moshi, and it's clearly the end goal is this. So for us, it makes a lot of sense to keep walking that path towards models where you really feel like there is a deep understanding, mutual understanding between you and the machine with whom you talk, and it makes the conversation very enjoyable, but at the same time, it's very useful. So you cannot just give up RAG and function calling and so on, because then you have a chit-chat buddy. And it's pretty fun and very natural, but it's kind of useless except a chit-chat buddy. So you want to have like a chit-chat buddy, but that can access the knowledge of the world and like make a lot of complex stuff. Exactly. Yeah.
Awesome. Well, thank you so much, Neil. Thanks for the presentation. That was my last question.
Thanks a lot.
So, all right. Let's give it up for Neil.
Thank you.
Awesome. Very excited for Qt. So before you leave, I would like to say one more thing. Hold on. Oh, sorry. Yep. I got a clicker here. Well, thank you so much for bearing with us and staying with us until now. I know it's been a long 2 days, but we're very excited for having you here. I personally really enjoyed this experience with you guys, so thank you. I'd like to thank every one of you. So thanks. Let's give it up for everybody here. All right. Look, this event wouldn't have happened without you, without your support, the support of the community, and the support of our sponsors. So I just wanted to thank everyone. So I wanted to thank Docker, Neo4j, Sentry, DeepMind, Arize, Algolia, and everybody else who supported us throughout this event. And we're super happy. Like, the quality of the speakers were just amazing. I don't know about you guys, but I really enjoyed it, and I had the front row to watch all those talks, and it's fantastic. But before you leave, we have 2 things for you. So if we're all gonna go upstairs by the expo, we're gonna take a group photo, and that's gonna happen in 3 minutes. And we have a very, very special announcement, so make sure to be around for that. Okay? So we can all walk together, and in 3 minutes, group photo and a special announcement. And thank you so much again. Bye. Woo! Yeah.